Stand by, here we go.
Welcome to Calculus 1. This is a refresher course designed for secondary high school teachers who maybe had calculus 10 or 15 years ago, or maybe even a little bit longer, and need to brush up on some skills. I currently teach AP Calculus BC, and I'm used to working with students who have experience with pre-calculus but don't have any experience with calculus. So I'm changing my roles just a little bit. So the kind of thing I'm going to be doing now in this course is not being quite as rigorous as I was, or as I am in the AP Calculus BC course. We're not going to be doing proofs in here. We're going to be doing some plausibility arguments. I hope a bunch of you just went, whew, because you remember the delta epsilon proofs from calculus as an undergraduate. We're not going to be quite that rigorous in this course, but we are going to be doing some plausibility arguments. Why does it work? And we are also going to be doing some derivation of formulas. So the detail in this course is probably not what you would have had you taken this as an undergraduate. With that in mind, the type of course that I'm teaching now is not the kind of course that I had as an undergraduate. When I was an undergraduate, my Calculus 1, Calculus 2, Calculus 3 was very analytical, very rigorous, very algebraic in nature. As a matter of fact, probably 2/3 of the points that I would have had taken off for a test when I was taking the course originally would have probably been for algebraic mistakes. Algebra is still pretty much a gatekeeper to calculus. There's still a lot of algebra that you need to do, but there's a lot more going on probably since about 1989, 1990, led by a few groups, in particular one out of Harvard, the Harvard calculus, where they got away from total analytic analysis of calculus and started looking at graphical methods associated with it, and started also looking at numerical methods related to the calculus. So as we go through this course, we're not going to hit just the analytical stuff. We're also going to look at graphical interpretation and numerical analysis, looking at examples and trying to find patterns from numerical examples. So as a textbook for this course, there are several textbooks on the web page that are suggested, but those are not certainly absolute. What I would suggest if you get a textbook for this course, look in the table of contents, look at the introduction, and see if there is a component in that textbook that addresses graphical, numerical, and an analytic focus on the course. And any textbook that says that it addresses those three should be good enough for you to use as a basis to follow along in this course. Another thing, well, since we're doing graphical, another thing that you will need to work with this course is a calculator. If we could go over to the calculator. There we go. I'm going to be using a Texas Instruments TI-83 Plus. You need a calculator. Let's clear that. You'll need a calculator that has, in this particular case, I'm going to choose that. You'll need a calculator, if you'll notice down here on the bottom, that does some numerical analysis, that gives you some numerical derivatives and numerical integrals. The TI-83, the 83 Plus would be good, the TI-89. There are plenty of Casio calculators, Sharp calculators out there. You just need one that's a little bit stronger than a scientific calculator if you're going to be able to do the graphical components to this course. Also, you will need a calculator that does good graphing. We're going to be looking at the graphs. It would also be nice if you have a calculator that has some programs. We have a couple of programs that we're going to use in this course. Let me turn it back on here. The two programs that I'm going to be using will be on the web page. If you go to the web page, it'll say and you can enter it into your calculator, or if you have some calculators, these are already built in. But those programs will be listed on the web page. Let's see. Oh, one other thing. On the web page will also be approximately 10 to 12 internet sites that we will have permission for you to go to, links that we'll have for you to go to, so that you can use it as a tutorial and practice for homework. There will also be some homework examples that you can work on the website that you can supplement your textbook with before you take the course, the unit tests in the course. So the first thing I want to start with then is what every teacher who teaches calculus starts with. We go back and look at some topics from pre-calculus. Generally, when I teach a calculus course, I'll start and we'll go back and do a pretty intensive review of pre-calculus, some trigonometry, some what you might call algebra 3 topics, finding roots of polynomials, things like that. We go back and look at those pretty intensely for a couple of weeks to make sure that we know what's going on with those. I'm going to sort of casually address those topics in here right now. The first thing is I want to talk about graphing on the calculator. So if I go to the calculator, let's get rid of that. My calculator, the TI-83 Plus, I've got this function that we're going to be looking at a little bit later. It was a hard one, so I went ahead and entered it in. I'm going to skip down and do another one. I'm just going to do equation y2. Let's just make it say x squared plus 1. There are several ways that I can look at it, and I've got a zoom feature right here. I'm going to mash this zoom button. The three features that I'm going to be looking at most intensely for this course would be, well, I'm going to use zoom in and zoom out a little bit, but the 4 is a decimal window on the screen. 6 is standard, and that's basically the one I look at most of the time. And then you have one, if you arrow down on my menu here, you have a zoom fit, which sort of does its best guess at fitting the program. So the first one I want to choose is 6, and look at the graph x squared plus 1. Notice it has a minus 10 to plus 10, minus 10 to plus 10 on the x and y axis, and it just gives you a nice picture. Notice it is not a square. It's rectangular, even though the units here, each little tick mark represents a unit of 1. They're not equally spaced on the x and y axis. If I do zoom 4, the nice thing about zoom 4 is it shows a little bit closer into the origin. It only goes out a little bit over 4 here, a little bit less than 4 there. But what happens here when I trace the little cursor here that I can move along with my cursor arrows, notice the ordered pair down here at the bottom for x and y. The x values are all tenths. They're not like square root of 3 or some irrational number or some decimal. So you can get some very nice ordered pairs that are fairly easy to work with. So we can see right here, we've traced this particular point right here. This point, it has the ordered pair 1, 2. But if you use the zoom 4 on this feature, the zoom 4 feature on this calculator, all of the x components are decimal places. So that's the zoom 4. The zoom fit, which is zoom, and I'm going to arrow down to the 0. You can just hit the 0. The zoom fit chooses its own best fit, and you get to see everything on it. Sometimes that's good. If you don't know exactly what features you're looking for, the calculator does its own little best guess. So for the calculator, graphing, let's go back to the y equals there. If I get rid of that little thing, and I'm going to go up and highlight this one so I can graph that one, I'm going to zoom fit on that one and see the particular graph that it gives me there. It's a slightly different graph than the other one. The good news about that is, again, it's its best guess. Notice it does show you the minimum right here. Those of you that remember your calculus know that maximums and minimums are pretty good. If I hit the zoom 4 for the decimal, it gives me a little bit better picture. So one of the things that we're going to be doing with the calculator is using the calculator to find our best picture. There's no definite algorithm for that. Sometimes you just have to play with it. You have to play with the window. You have to figure out what your x values, your domain has to be. You have to figure out what your range has to be so that you do get a good picture. So one of the things that we're going to be doing fairly informally is when we make a graph, we're going to look at the graph. We're going to try to find as much about the graph as we can from the calculator. The next thing I want to look at is polynomials. So a little bit of review on polynomial graphs, in particular the power functions, and just a little bit of a pattern here. Y equals x, these are some graphs that you ought to sort of have in the back of your mind. They're Algebra 1, Algebra 2, Algebra 3 graphs that maybe you haven't seen in a while. But y equals x is just a line through the first and second quadrant where the ordered pairs are like 1, 1, 2, 2, 0, 0, the origin, maybe something like -3, -3. Okay. Y equals x squared, you know, is a parabola shape. Vertex at the origin 0, 0. Y equals x cubed. Y equals x cubed, I'm not really good at graphing freehand like that, but you can see it's, well, if you remember even and odd functions, you can see this is an odd function. It goes through the origin 0, 0. The connection I want to make here is this one and this one. The exponents, that's y equals x to the 1. The exponents are both odd here. If we look at one more, y equals x to the 4th. Let's see if I can get this one in here also. Y equals x to the 4th. Let's go to the calculator and graph this one. Y equals x to the 4th. I want to take that one off. I'm going to come down here, clear. X to the 4th power. It comes down and looks like a parabola. It is not a parabola. Parabola is the equation, is a graph of a quadratic function. This is not quadratic, so it's not a parabola, but it's parabola-esque, if you will. It has a parabola look about it. It's a U shape. Let's change it to y equals x to the 6th and get another even exponent and graph it. Notice it's got the same look. I don't know if you can make the connection, make the contrast. This is a little bit flatter down in here. If we do a zoom in, which is a 2, and I'm going to zoom in on that, you can see that it's, when it comes down here, it's fairly flat. There's not much distinction, at least on this scale, between the graph and the x-axis. And if we do a y equals x to the 8th, I'm staying with the evens. Now the even exponents graph, notice it does exactly the same thing. I'm getting a lot of U shapes. So if we look at y equals x to the 4th, y equals x to the 6th, y equals x to the 8th, we see a general pattern of what's happening. Now, one of the things that I want to comment on right now, because we're going to look at a little bit different in a minute, is that all of these coefficients, the lead coefficient is a positive number. But what's happening is all of these are some sort of a U shape if it's an exponent. In contrast to that, look at the, if you remember for the odd exponents, x equals 1, x equals 3, y equals x to the 5th, for instance. you're going to get some type of a function that starts down at negative infinity here in the third quadrant, and does a little curve, does a little action somewhere in here, and then goes up to positive infinity. Not a U shape. If you graph this and you stood back very, very far, went across the room and looked at it, there's not much difference between the general shape of x to the fifth as a graph versus x to the third power as a graph versus x to the 1 as a graph. You go from the third quadrant up to the first quadrant. Now, what thing do I want you to remember from this is the general shape of polynomial functions. The general shape of polynomial functions are going to be based on the biggest exponent. And if the exponents are positive, y equals x to the odd exponent is going to end up doing something like this. Again, the coefficient is positive here. And if you have y equals x to the even exponent, 2, 4, 6, 8, 10, 12, you're going to have something that's a little bit of a U shape. So keeping those little things in mind, those little pre-calculus concepts in mind are going to help us a lot. If we make the exponents even or odd like we've done, but we make the coefficient negative, what's going to happen? Well, let me see if I can do that in red as a little bit of a contrast. If I have a negative exponent right here, instead of going from the third to the first quadrant, it'll be going downhill. If you remember negative slope, y equals x to the 1, y equals negative x is a line slope of negative 1, and slopes go downhill. Negative slopes make the line go downhill. If this one is a negative number as a lead coefficient, it's not going to be a smiley face. It's going to be a frowny face. It's not going to be a cup. Cup is from positive. It's going to be a cap shape. So another little thing to remember from pre-calculus is the general shape of polynomial functions when you graph them. The next thing I want to talk about then is finding roots or zeros of a function. Let's look at a particular function here. Y equals x cubed minus 2x squared minus 1. That's one that doesn't factor. You remember if you have one that factors, you can factor it and set the roots equal to 0. That's a fairly easy thing to do. I want to address something that doesn't factor, that doesn't have a nice little graph on it. And how do we actually find, it doesn't have a nice little factorization, doesn't have nice roots, and how do we actually find what the graph is? Well, what I'm going to be doing, you remember your rational root theorem that says if it does have a rational root, or a root that's either an integer or a rational number, you can take the factors of this number over the factors of the lead coefficient, and all those combinations are at least your potential candidates for roots. What I want to do is take this particular function and find graphs on the calculator. Now, this is something that you need to do with your calculator. You need to be familiar with how to do this with your calculator. So I'm going to say x to the third power minus 2x squared. What was that? Minus 1. And I want to give a little graph for this thing. So I'm going to find a nice little graph. Now notice it was a cubic function. Since it was the lead coefficient was cubic, you notice we're starting down here in the third quadrant and we're sort of going up to the first quadrant. So it's got that same general shape. It's got this little hump in here, but we'll worry about those later. To find the root or the 0, I want to find out exactly where it crosses the x-axis. One of the problems is sometimes you can't find out exactly where it crosses the x-axis. There are two things that you can do, though. One is a good thing, one is a bad thing. The good thing is to find the exact answer, and a lot of times we can't find the exact answer. I know sort of a standard rule, AP Calculus Standard rule is if you give me a solution in decimal form, you give me at least 3 decimal places. Sometimes word problems, if it's a particular word problem, say involving money, you only have to round it to 2 places for cents. If it's a problem involving some particular kind of answer, you might need 5 or 6 decimal places. The rule of thumb that I'm going to use, I'm going to borrow it from the AP Calculus sequence, is to use 3 decimal places. You can either truncate to the 3rd decimal place or round to the 3rd decimal place, but I'm sort of familiar with that, so that's the one that I want to use. If we'll go back to the calculator, I want to look at that little point right there and find it. Now, I have a trace button, and I just hit the trace, and notice trace, all graphing calculators have some type of a little trace button. I want to find out exactly when the y is equal to 0, and notice if I trace it, I'm not getting the y equals 0. I'm getting very close. So one caveat, one danger that you can make is if you just use trace, you're not going to get the exact root. The root looks like it's between 2.2 and 2.3 because notice the y goes from a negative value to a positive value. So it's somewhere between 2.2 and 2.3, but that's not nearly accurate enough. So what I'm going to ask that you do is find something on your calculator. I did second trace on mine, and select 2. 2 will find the 0 of the function. We'll find the place where it actually crosses the x-axis. A left bound, I need a point below that. The right bound, I need a point above that. And I just let it says give a guess. The guess makes it a little bit easier. I just always use the second value. And notice what happens there is it gives you the root y equals, let me copy that, 2.2055. So I would either write that as 2.205 or 2.206. Either one of those would be fine, acceptable as answers. This 3rd decimal place, you can either, if it's giving me 3 decimal places, you can either truncate or round. It does not matter. But I would accept both of those as answers. So I know that's not the exact answer, but I'm going to end up saying x is equal to that, even though I know it's not exactly equal to that. I'll say x is equal to either 2.205 or 2.206. Knowing in the back of my mind that it is actually not equal to that, but we'll accept that as an answer.
Your mic slipped.
Okay, where did... Is that all right? That's
good.
Thank you. Okay, the next thing I want to look at, we're still doing some pre-calculus stuff here. We're still looking at some pre-calculus concepts. One from Algebra 1. A lot of this is from Algebra 1, actually. Y minus y1 equals mx minus x1. A nice little review. What is this? It's the equation, it's the formula that if you know an ordered pair, x1, y1 for a line, and you know the slope m, then you can use this formula to insert the slope and the values x1 and y1 to find the equation of a line. It's the point-slope equation of a line. So as a simple little example, if I say a line goes through the point 2, 3 and has a slope of 4, then the equation of the line is going to be y minus 3 equals 4 times x minus 2. A simple little substitution in there gives you the equation. This would be acceptable to me. There's a lot of, a couple of more steps in here. Y minus 3 equals 4x minus 8. Y equals 4x. Let's see, you add 3 to both sides, minus 5. It's the same equation. These two are the same equation. So, as a nice little reminder, the point-slope method. With that, we're talking about slope of lines. There are two types of lines that I want to remind you about. One, that lines are parallel, and one where lines are perpendicular. And see if you can remember what do you know about the slopes of those lines. Well, if two lines are parallel, they have the same slope. If two lines are parallel, their slopes are the same. If two lines are perpendicular, there's several things, there are a couple of ways of writing it. If I have a slope m1 and there's another slope m2 where these two are slopes of lines that are perpendicular, then m1 times m2 is equal to -1. There's an easier way of saying that. The slopes are negative reciprocals. And if the slopes are negative reciprocals, that means, for instance, if I have a line whose slope is 2, let's say m is equal to 2, then if I come down here and make any line that is perpendicular to it so that the two lines intersect and form a right angle, then the other slope of the other line would be -1/2. So we're going to be using parallel lines and perpendicular lines. And again, a lot of what we're looking at right now is just a little review so that you can know what we're going to be using. The next thing I want to look at is the distance formula, the distance between points. And there are actually three things that are all exactly the same thing. There's the Pythagorean theorem, there's the equation of a circle, and there is the distance formula. The distance formula, the distance between 2 points, is that big square root thing, x sub 1 minus x sub 2 all squared plus y sub 1 minus y sub 2 all squared. That is mathematically exactly the same thing as the Pythagorean theorem. If you square both sides, you get d squared equal to x1 minus x2 squared plus y1 minus y sub 2 all squared. That's in the same formula as the Pythagorean theorem, which is x squared plus y squared equals r squared, where a squared plus b squared equals c squared. Leg squared plus leg squared equals hypotenuse squared. Notice that is also basically the equation of a circle whose center is at the origin. X squared plus y squared is equal to 9, for instance, where r squared here is 3. X squared plus y squared equals 9 is a circle whose center is at the origin, whose radius is, well, close enough on a circle there, whose radius is 3. So, as a little bit of review, the distance formula, the Pythagorean theorem, and the equation of a circle, we're going to be hitting those quite a bit. The last thing I want to mention as sort of a pre-calculus concept is a little bit of trigonometry. I want to hit on a little bit of trigonometry. The trigonometry I want to hit on are the little things that you have to remember. The first thing I bet you can guess what the first thing is. The first thing is when we look at angles in calculus, we want to work in radians. The reason is it enables us when we get over to the chain rule not to worry about the derivative of the sine being the cosine. Radians make things work out very nicely. So we want to be using radians. The second thing is if you happen to have something in degrees and you need to change it to radians, there's a nice little ratio and proportion for that. If you take the number of radians and you put it over a complete circle, which is 2 pi, and set that equal to the number of degrees, okay, there we go, and set that over 360, that's a nice little ratio and proportion that you can use quickly. As a matter of fact, I can do it this way a lot quicker than I can find the right buttons to mash on my calculator to convert it. Radian measure over 2 pi, which is the number of radians in a complete circle, is equal to the number of degrees over 360. Now, some people like to cancel the 2 out here and make that 180 and say radians over pi equals degrees over 180. But that's a nice little, if you know radians, you can find degrees by cross multiplication. If you know degrees, you can find radians by cross multiplication. So that's the little trick I use. So one of the things that I like to do with my students, and I'm going to suggest that you possibly do it too, is you get a little series of 3x5 cards. And every time we get one of these little memorable little formulas, that you write it down and keep it in the back of your book. That way when you get stuck, you'll know always to look for the little card in the back of the book, and it's sitting there waiting on you. Okay. The next thing is on calculus, on the pre-calculus, on the trigonometry, are some identities. And the big identity is the Pythagorean identity, sine squared plus cosine squared equals 1. We're not going to do any derivation of that. It's a pretty standard one, sine squared plus cosine squared equals 1. But if we look at sine squared of theta plus cosine squared of theta equals 1, there are two other little variations of that we can find. One, and to be honest, this is the only one I remember, and every time I need the other ones, I have to derive them. So if I just take the sine squared of theta and divide it by the sine squared of theta plus cosine squared of theta divided by sine squared of theta equals 1 over sine squared of theta. So we're taking the original Pythagorean identity up there, sine squared plus cosine squared equals 1, and dividing every term by sine squared. Then that gives us 1. Now, cosine over the sine is the cotangent. That's the cotangent squared of theta. And 1 over the sine is the secant squared of theta. So this is another little Pythagorean identity, not a triple, excuse me, an identity that'll pop up. The same thing, instead of dividing through everything by the sine squared, if you divide everything through by the cosine squared, you have sine squared theta plus cosine squared theta equals 1. Divide everything through by the cosine squared theta, cosine squared theta equals 1 over cosine squared theta. Then that becomes sine over cosine is tangent, so that becomes tangent squared theta plus 1, and that becomes, oops, I made a mistake back up here, didn't I? Is this a mistake? No, wait a minute. 1 over the cosine is the secant squared. This, yeah, I did. This is the cosecant. 1 over the sine is the cosecant squared. Thank you. Secant squared theta. And this is the other one. You have to know your trig identities to be able to do this. Obviously, I don't. Tangent squared plus 1 is equal to secant squared. And this is one that's going to this is probably going to be the big number 1. This is going to be number 2. And this is going to be number 3 in the amount that we use them. So those are 3 little identities that you need to keep in the back of your head. Now, with that, there is another, they're called the double angle and the half angle formulas. Again, we're not going to derive them. But what I do want to look at is another way of looking at the cosine squared theta and the sine squared theta. If we look at cosine squared theta, a lot of times this is going to end up being, if we have y equals this, it's a composite function. And composite functions sometimes give us a little bit of difficulty when we're trying to take derivatives or antiderivatives. So that the fact that you got a cosine and a square in there, a lot of times it would be nice to get rid of the square and keep the cosine, or get rid of the cosine and keep the square. Well, that's pretty impossible to do. So if I can get rid of the square and keep the cosine, I would be happy. So it happens to be a little half angle formula. 1 plus cosine of 2 theta over 2. This is a nice little 3x5 card you need to keep in the back of your notebook, or keep a little sheet of formulas maybe. This one, my students and I argue over this. I say these two are only one formula because if you know one, you can remember the other. For the sine squared, it's going to end up being 1 minus the cosine of 2 theta over 2. So for the cosine squared, the values are the same. It's just here we're adding, here we're finding the difference of the two terms in the numerator. These are two things that are going to pop up quite a few times in the process of this course. So those are a lot of nice little pre-calculus things. I hope you recognized them. If you didn't, you probably need to go back and spend a little time looking at them. I don't think you need to worry about being able to derive them or find them, but that's just some highlight topics for pre-calculus. The next thing I want to talk about then is I want to go into the first thing that actually this topic right here caused both Leibniz and Newton quite a bit of difficulty when they came out with the calculus. Newton had something called infinitesimals. And a lot of people didn't like those, especially a lot of the religious community, because this was a time still when, well, the Protestant Reformation had been going on for a couple of hundred years, and there was still a lot of religious angst in Europe going on. And the Protestants, a lot of the Protestants were very, very strict, very, very rigorous. The good Protestant work ethic was starting. And Newton got a lot of criticism about the calculus because of working with the infinite, because a lot of the Protestants, the ministers, were talking about things like only God is infinite, and Newton had no business trying to figure out what God was trying to do with his infinities. And this was one of the big problems with calculus. Well, infinitesimals turn out to be really this concept that we're going to be talking about, the concept of limit. And limit was sort of the concept is easy, but the definition was hard. Probably, early 1800s, a little bit after Napoleon, Cauchy, I guess, was probably the one who first, which would, a good time after Newton was dead, probably came up with some of the basic ideas of turning this into what we now have as rigorous mathematics, a little bit more rigorous mathematics. So what I want to talk about now is the concept of limits. We're going to make a few definitions, do a lot of examples, and go from there. So let's look at this concept of limits. If we look at limits, again, intuitive, we know what limits are. Y equals x squared, we know that's the nice parabola. The origin is the vertex. And I want to look at this little point right here. Well, this little point right here happens to be the ordered pair to 4. Notice my graphs are not to scale, but close enough. And what we want to talk about this limit, and in this particular case, it's a fairly, it's probably a little bit too simple example. I'm asking the question on the graph, and I'm looking at all these little ordered pairs along here on the graph. As x gets closer and closer to 2, what happens to y? Well, there's a nice little thing that's going on here. If I get closer and closer and closer to 2, if I look at ordered pairs that are closer and closer and closer to 2, if the x component is closer and closer to 2, it's pretty obvious that the y value is getting closer and closer and closer to 4. And that not only happens from the left-hand side, it also happens from the right-hand side. Now, we can see that numerically if we just make a little chart. Let's look at a nice little chart here. Let's look at some x values. Let's say 1.98, 1.99, 2, 2.01, 2.02. Let's look at these values because these are some values that are pretty close to 2 from the left-hand side. And these are some values that are pretty close to 2 coming in from the right-hand side, 2.1, 2.01, 2.202, 2.012. And let's look at the function that was y equals x squared. Now I'm going to need my calculator here to get some value. You don't have to go to the calculator. Let me just do 1.98 squared. Oops, I got to turn the calculator on. 1.98 squared is 3.9204. And 1.99 squared is 3.9601. Now, notice I said as I get closer and closer and closer to 2. I didn't say anything about actually getting to 2, so I'm just going to hold off on this value right here. Because as far as the limit's concerned, that value really is not that important. Let's try 2.01 and square it. And I get 4.0401. And if I get 2.02 and square it, I get 4.0804. Now, notice as I'm above 2, I'm getting values a little bit above 4. And if I'm below 2, I'm getting values that are a little bit below 2, but they're getting closer and closer to 2, 3.92, 3.96. Well, obviously, we know 2 squared is 4. What we're looking at as at a limit is if I go from the the left-hand side, which are the numbers less than 2, and if I come in from the right-hand side, which are the numbers a little bit greater than 2, if I get closer and closer to 2, is there a little target number in there that I'm going to hit? Well, if I look at it numerically, I've got a little bit of a problem. Because you can't always numerically look, you can get intuitive ideas. You can get an idea that, yeah, maybe it looks like it's going to this number. There's an interesting little book that has an interesting little paragraph in it. This is a great book for teachers. I've read it a couple of times. It's just a fun little book. It's called The Joy of Pi. It's by David Blattner. I'm not trying to sell it. It's just got some very, very interesting things. It's Walker Publishing. And there is a website, www.joyofpi.com. It'll be on our website if you want this reference. But it talks about a little paragraph in here I'm going to read to you about Brahmagupta, who was an Indian mathematician. If those of you that have had some advanced geometry, a little bit more geometry than a high school student, if you can remember it. He was one of the Indian mathematicians from the 7th century. And it says right here that he took a tact to find the value of pi. Obviously, that's what this book is about. And what he did was he looked at, if you'll look at the drawing again, he was trying to find the value of pi, the ratio from the circumference to the diameter or the radius of a circle to the circumference, trying to find that ratio. And he did it much like the Aristotle problem, the Aristotle solution was. He looked at inscribed polygons. And so what he would do is he would inscribe a polygon, and he would try to find that value. Then he would inscribe a polygon with more sides in it. And he would get closer and closer and closer. Well, this gives the values. It says first he calculated the perimeters of inscribed polygons with 12, 24, 48, 96 sides. So he would inscribe the polygon. We saw he would inscribe a dodecagon. He would inscribe a 24gon. He would inscribe a regular 48gon and a regular 96gon. And he would try to find the perimeter of the polygon. And what he discovered was that if he had, if we say insides right here, that this was the square root of 9.65. 24, he got the ratio as to be 9.81. Here you got the ratio, the square root of 9.86. And for 96 sides, he found the ratio to be 9.87. And he had a nice little pattern here. He had this little pattern going up, square root of 9.65, 9.81, 9.86, 9.87. You know, hindsight is 20/20. What he made as a statement was that the more sides you get, now remember he was trying to go to infinity here, the more sides you get, the more this number is getting a little bit bigger and a little bit bigger. So he just made a wild guess and he said, boy, it looks like it's the square root of 10. So he established pi as, for the most reasonable value, the square root of 10. Now we know that that is not true. It's pretty close actually. if we look at the square root of 10. It's probably not a bad estimate for pi. But one of the problems that I'm trying to make with this example is that a lot of times you can see this number pattern and you can see what looks like might be the limit, the target number right here. Well, we know that's probably a little bit too big. If you compare the square root of 10 to the calculated value of the square root of 10 to the value of pi, you'll find out that pi is a little bit smaller than that, I believe. If you go to the calculator, let's hit, let me clear that. If we hit pi, we get that as a value, and if I hit the square root of 10, 10 to the 1/2 power, we get 3.16. Pretty close, probably pretty close for 7th century mathematicians, but certainly not accurate enough for what we need for today. So, as a caveat on finding limits, as a caveat on finding where these limits need to go, what the limit is, you need to be careful if you're looking at numerical examples. Okay, I just lost myself, so give me a second. Here we go. If we go back to the little example, y equals x squared, and we look at that point right there to 4, we can write some notation. We're going to use some math notation here. And I'm going to say the limit as x approaches 2 of the function x squared is equal to 4. Now, by far the majority, well, all polynomials, and by far a lot of functions, the limit can be deduced by a simple substitution, and this is an example of that. Simple substitution, all you have to do is you take the value of 2, you put it in here for the value of x. You're saying x is getting close to 2. 2 squared is 4. The limit is actually 4. If we want a general term for this, we would say the limit as x approaches some value c of the function f of x is equal to L. Now, for the limit to exist, L here has to be a real number. We don't want it to go off to infinity. And one of the problems that we're going to be talking about in a little bit is what happens if this value right here turns into that 0 over 0 value. A lot of calculus has been described to me before as figuring out what is 0 over 0. Because 0 over 0 is not undefined. If you remember the little thing that you teach the Algebra 1 students, the Algebra 2 students, something about 5 over 0 versus 0 over 0. 5 over 0 is undefined. It has no meaning. 5 over 0 has no meaning. If I try to divide 0 into 5, I can't get an answer. It won't go 10 times because 10 times 0 is 0 and the 5. And remember, the remainder has to be less than the divisor. So there's no quotient I can put here. 100, a million, 1,000, billion, a googol. There's no value here that I can get a remainder down here when I subtract. The problem with this is not the same. I can say 0 goes into 0 one time and I'm fine. I can say 0 goes into 0 two times and I'm fine. I can say 0 goes into 0 1,000 times and I'm fine. The problem with this is 5 over 0 has no answer. We call it undefined. 0 over 0 does have an answer. The problem is it's got an infinite number of answers and we don't know which one's the right answer. So we say that is an indeterminate form. And one of our goals here with limits and other things that we're going to be seeing in calculus is when we have this 0 over 0 form, how do we figure out is one of these the right answer that we're looking for? Which one is the correct answer? So as we look for limits, we're going to be stymied a little bit by this, but we're going to be finding some techniques to work through it. Now, a few little definitions about limits. And these are probably going to be on almost the first or second page of any calculus book that you have about properties of a limit. And the first property of a limit is the limit as x approaches any value c of a constant function is that constant function? Well, let's put a little dotted line right here for the formula, the function y equals 5, a horizontal line. I don't care what value of c I'm getting close to on the x-axis, the value for the y-axis, the y value is always going to be 5. So the limit of a constant, no matter where you're going, the limit of a constant is a constant. Another biggie is the limit of x as x approaches c is equal to the value of c. Well, that makes sense. If we look at the function y equals x, all the ordered pairs on this line are the two numbers are the same, so that would be like 5, 5 or 2, 2. As x gets close to c, x gets close to c. So the limit of x as x approaches 3 is 3. And whatever number this is, that number is going to be exactly the same number. Now, we're going to use that in association with a coefficient. And I'm going to say the limit, let's say my function is now 5x. I'm hung up on this number 5. I can't get off of it. X approaches, say, 2. What's this going to be? Well, the obvious thing that we can do is just substitute 2 in there and get 10. We know that. The other thing I want to mention, though, is if I have a coefficient like this, a numerical coefficient, doesn't have to be a nice whole number, it can be a fraction or an irrational number or anything, I can take it outside, I can factor it out, and say that's 5. Of course, we just looked at that 2 times, that's 2, and we can get 10 that way. Now, this is probably the easier way to do this is just to say 2 substitutes in there and gives you a 5. Times 2 is 10. But sometimes you have a particular problem like this. Maybe you have the limit and your function is x plus 2 times x minus 7 as x approaches 3. And you can do a nice substitution in there. What we could also do is split that up and say x goes to 3 of x plus 2 times the limit as x goes to 3 of x minus 7, and split the product up. The caveat you have to worry about here, it works for, well, of course, if it works for that, if it works for multiplication, you would also think that it works for division. So let's say I have some function f over some function g, f of x over g of x, and x approaches some value c. What's the problem that I have to worry about here? And this is where we're going to get, we're going to really address this on the next tape. What happens if this value right here, if I put c in here for this g function, if that value is 0? What happens if I go there? Well, that's going to be the next big topic. I would suggest that you find your calculus book and review properties of limits. We're going to be using those quite a bit. Again, they're not that difficult and they're pretty obvious. The limit of a sum is the sum of the limits. The limit of a product is the product of the limits. The limit of a quotient is the quotient of the limits. All you have to do is basically a substitution, unless you mess up and get this 0 in the denominator. And more importantly, what happens if we also get a 0 in the numerator? So I'm going to stop tape 1 right now, and we'll start up in a minute with tape 2. Welcome to lesson 1, tape 2. We're doing calculus refresher, and last tape we got as far as starting to talk about limits. Now, we haven't made a formal definition about limits yet. We've been making some sort of intuitive concepts, some intuitive notions about it, some things that we need to know, some things that we need to do. One problem that I've got in teaching this course is I know a lot of you that are taking this course have already had this course, and this is refresher. So I'm trying not to be too detailed. I'm trying to give you the refresher stuff, not go back and do the rigorous, detailed notation, although notation is important. I'm not trying to get away from that. But what I am trying to do is not to be too pedantic and assuming that you have some recall of this knowledge. So I'm trying to cut a fine line in there. We were talking about limits, and what I want to do first of all is look at some concepts, or excuse me, some properties of limits that I suggest that you find in your in the calculus book you're using. And if we can look right here, the first little theorem or property or rule or law, whatever you want to call it, is if k is a constant, you have k times some function. So this might be like 5 times the function would be x, like 5x. So an example of this would be, say, the limit as x approaches 2 of a constant 5 times some function x is equal to what this property says right here is if it's a constant, I can take the constant out, factor it out, limit x approaches 2, compute this limit, and then multiply the answer by 5. Well, the limit of x as x approaches 2 is 2, so that would be 10. Again, it's real simple just to take the 2 and do a substitution in there to find the value of the limit. A lot of those can be done that way. So as x approaches some real value c, we get an actual limit. The next one would be the limit of a product. Excuse me, the limit of a sum. This is the sum, I'm sorry. The limit, again, I'm starting to leave out the x minus c because I don't want the notation to get too crowded, but x, we need to have some x approaches some value. If I have a sum of two functions, what this says is I can split the two functions up individually, find the limits individually, and then add them together. Again, this works for the sum, and it also works for the difference. So if I have something like the limit as x approaches 2, oops, let me clean that up, of 5x squared plus 3x, what this says is I've got one function here, one function here. I can compute this one by itself. I can compute this one by itself and then either add or subtract them together. So 2 squared is 4, 5. That would be a 20 from this part. And 2 goes into, 2 goes for the x there, 6. So I can compute that part and then add them together and get the limit of 26. The limit would be 26. The same thing is true for a product. The product of the limits is the limit of the products. If I have two functions that I'm multiplying together and I multiply them together and then take the limit, that would be the same as taking the limits individually and then multiplying them together. The same thing is true almost for a quotient. If I have a quotient, some function f divided by some function g, and I take the limit as x approaches some constant, then if I take the limit of the numerator and the limit of the denominator individually, and then I can divide them, as long as the limit of the denominator is not equal to 0. If the limit of the denominator is 0, I tend to have a problem, and we're going to address that issue in this tape. We're going to look at what happens when that denominator becomes 0. As we look at this, the first thing then I want to do is look at a fairly rigorous little definition, notation. And let's look at, say, a function f of x has a limit as x approaches c, c being some constant value, some real value, IFF, that means if, that's my abbreviation for if and only if. If and only if. I'm going to introduce two new terms here, the right hand limit and the left hand limit both exist and are equal. So, definition of a limit: a function f of x has a limit exists as x approaches some value c if and only if. Now, if you remember from your geometry, if you go back to proofs in geometry, if and only if means the hypothesis implies the conclusion, and it turns around for the conjugate. The conclusion implies the hypothesis. So that means if I have this part, then I have this part. Also, if I have the conclusion, it means the hypothesis is true. If and only if the right-hand limit and the left-hand limit exist, they have to exist, meaning it has to be a real number, not infinity, not some weird value, but some real number, and are equal to each other. Now, what I want to do with this definition is talk about what a right-hand limit is and a left-hand limit is, and talk about some of the little things that go with them. A right-hand limit is, of course, going to be a limit coming from the right-hand side, and a left-hand limit is going to be a limit coming from the left-hand side. So if I want to look at a particular function, and we sort of looked at this a little bit with that y equals x squared on the last tape, let's look at a graph. Oh, that looks like that. I don't know what it is, but here's an ordered pair on the graph. And let's call that 1, 2, 3, 4, 5, 6, and let's call that 2. Let's call that ordered pair 6, 2. This is a nice smooth curve. As a matter of fact, our next topic is going to be looking at something called continuity. But this is a nice smooth topic. We're building up the concept of a limit before we go to the concept of continuity. And there's this nice little point right here on the graph. Well, if I talk about the left-hand limit, what I'm talking about is what is the limit as I approach from the left-hand side. That means for this function right here, for this graph, which contains a lot of ordered pairs, as x gets closer and closer to 6 from the left-hand side, what happens to y? Well, if I approach it from the left-hand side numerically, what I'll be looking at is 3, 4, 5, 5.1, 5.2, maybe 5.9, 5.99, 5.999, getting in there really, really, really close to 6. What's happening to the graph? What's happening to the y value as I get close to x from this side? Well, what's happening is obviously is getting closer and closer and closer to 2. So the way I would write that, let's see if I have enough room down on the bottom of this little piece of paper here to write that. I would write the limit as x approaches 6. Now, I'm not approaching 6 in general, but I'm approaching 6 specifically from the left-hand side. So that's the side where the negative numbers are. It's the left-hand side. So I'm going to write a little exponent-looking thing right there with a negative, and that tells me I'm approaching 6 from the side of the negative numbers, or the left-hand side of this function f of x is equal to 2. And that would be my left-hand limit. Now, if I do the same thing from the right-hand side, instead of coming up from the 5 side, I'm coming down from the 6 side. So I have 8, 7, 6, and I'm coming into 6, letting 7, 6.9, 6.8, 6.1, 6.01, 6.001, 6.0001, getting closer and closer. And I'm looking at what's happening from this side. What's happening to the y there? Well, what's happening to the y there is pretty much the same thing that was happening from the left-hand side. The way I would write this right-hand limit would be the limit as x approaches 6 from the right-hand side of my function f of x. Notice all I have is the graph. I don't know exactly what the equation for the function is, but that's not particularly relevant here, is equal to, again, 2. Because as x gets closer and closer and closer to 6 from the right-hand side, top down, coming in this way, My y value is getting, it looks like it might be about 2.5 right here, but it's slowly coming down, and the y value is reaching the 2 right there. So I can see from the left-hand side and from the right-hand side, both values are 2. Now let's go back and look at the definition and see what the definition says about this. A function f of x has a limit. It has an overall limit as x approaches c. In this case, c was the 6. If and only if the right-hand limit, which was 2, and the left-hand limit, which was also 2, exist. Well, they both exist. They're both 2 and are equal to each other. And of course, 2 is equal to 2. So we can say in this case, this function has a limit as x approaches 6. So I've got a left-hand limit, I've got the right-hand limit right here. I've got the left-hand limit that I'm writing again of f of x is equal to 2. So here's my right-hand limit. Here's my left-hand limit. Notice they both exist, and the right-hand limit and the left-hand limit are equal to each other. So I can say the limit as x approaches 6 of this function is equal to 2. Well, this is always going to happen if it's a nice smooth curve like this, if it's a nice polynomial. Polynomials are fairly easy to look at. We're going to look at a few that maybe have a little bit of a problem in it as you go along, and one of them is over here on my calculator. So if we look at the little calculator, I want to look at, let me get rid of that second one. That one might be a little confusing. I want to look at that particular function. That particular function, I've already entered it in because I'm a slow enterer. X cubed minus 7x squared plus 17x minus 15 divided by x minus 3. Now, those of you that know what's going on here, and I'm certain all of you do, are looking at that thing and you see that it's a rational expression. You have x cubed minus 7x squared plus 17x minus 15 in the numerator, and x minus 3 in the denominator. Could we get a shot of the overhead for just a second? Right here. This is my function. Y is equal to that particular function right there. And everybody in here knows that something goes on with this little thing in the denominator. We know it is undefined when x is equal to 3. So the question I'm going to ask, if this is the function, well, let's call it f of x. If this is the function, what is the limit as x approaches 3 of this function f of x? Now, our first problem here is, in contrast to the last one where it was a nice smooth function, we know something sort of nasty happens here. I'm not exactly sure what happens here, but I know something happens here. Well, let's go back to the calculator and let's actually graph it. So if I'm back to the calculator, I'm getting ready to graph this thing, and I'm going to just graph it as a zoom 6. Now, here's a bit of a problem. It's graphing it, and it looks like a nice little parabola. Well, it was an x cubed over an x, and if that cancels, that gives you an x squared. So you expect something parabolic. But the problem is we've got a problem here at 3. 1, 2, 3. Something should be messing up right about there for x equals 1, 2, 3. So I'm going to try to trace it a little bit and see if I can get to, that's 2 right there. It's a little bit over 2. I'm going to try to get something over to 3. Notice if I just do a little simple trace, it doesn't hit 3. It jumps from 2.97 to 3.19. So the problem with my calculator here, and again, we've got to be smarter than our calculator, is our calculator's not telling us the information that we need to know. So what I want to do is force my calculator. I'm going to do that. If you remember the zoom 4 for decimal, if I zoom 4, it's going to graph it. And notice something does happen when I get to x equals 3. It gives me a little hole in the graph. Well, that little hole in the graph means something is missing. So this is not a function that is a nice smooth function. I've got a little hole in the graph here. And as I look at the hole in the graph, I'm going to say, what happens? Well, if you go back to the definition, notice the definition said nothing about f of x existing. The limit from the left had to be equal to the limit from the right. They had to be approaching the same value. It didn't say that value had to be there. It just said I had to get closer and closer and closer here, and I had to get closer and closer and closer here as I go, but it doesn't say my target actually has to be there. So if we go back to the calculator, and I'm going to do a little bit of a trace here, and let's do the trace starting at 0. Notice my ordered pairs down here. It's going to come down. There we go. I get the ordered pair 1, 2. I'm getting all these nice ordered pairs. It looks like I have a vertex somewhere right about there. I don't know that for a fact, but it looks like it. It's going back up now. Notice what's happening as I get closer and closer and closer and closer from the left-hand side. 2.6, I'm getting 1.36. 2.7, I'm getting 1.49. 2.8, I'm getting 1.64. 2.9, I'm getting 1.81. Now if I hit it again, it's going to give me 3 for the x value, and of course we know there is no y value. There's a hole in the graph right there because of that x minus 3 in the denominator. But as far as the limit is concerned, that's totally irrelevant. I don't need that value there. If I go to 3.1, notice I'm getting a little bit bigger than that. So what I'm saying here is if this looks like it's a nice smooth curve, I'm somewhere between 1.81 and 2.21. Well, if we just took an average, it would be 2, and that's probably a nice guess for that. So let's go back to the overhead, and let's look at this little graph right here. It looks something like that, where this little point right here, 3, I approached 3 from the left-hand side. Well, the left-hand limit, the limit from the left-hand side is getting closer and closer and closer to this little value. The problem is, I'm trying to mark that in red. Maybe it's not showing up, so I'm going to draw a big circle. That circle means that little point's missing. I'm getting closer and closer and closer to that circle. I'm not ever going to get there because that point doesn't exist. The same thing is happening from the right-hand side. I'm coming down here closer and closer and closer and getting closer and closer and closer from the right-hand side, and I'm approaching the same target value. The limit exists. Whatever that little hole in, whatever that hole in the graph is right there, is my actual limit, because the limit from the left, my target from the left, is equal to the target value from the right. Now, the question is, how do we figure out this? Because I think we just looked at the calculator, and we found out that it was between 1.81 and 2.21. Now, the obvious guess is that it's 2, because we like nice whole number mathematics. Let's go back to the calculator, and I want to do something with the calculator. I'm going to do a table set. I want to start at a value. I'm going to make a table of values instead of figuring out by hand. Our target value was 3, so I'm going to do about a 2.9. I want to start at 2.9. And I want my value to be 0.01. That's my increment value. And let's see if I can actually find the table that starts at 2.9. Remember, the 2.9 gave me a 1.81 from a while ago. So now I'm doing increments of a 100th, 0.01. And notice what's happening here. 2.91 gives me 1.82, 1.846, 1.64, 1.88, 1.9. I'm getting a table of values here that are getting closer and closer and closer to some magical value, 2.99. Now 3, of course, that should give me an error because when I substitute 3 in the denominator, I get 0. And notice as I go to the right-hand side, the values are coming in 2.08, 2.06, 2.04, 2.02. So now I've used the table on the calculator to narrow it down not between 1.8 and 2.1, but between 1.98 and 2.02. I can get actually closer if I go back to my table set, start at 2.99 and make my value 0.001. Now my increments are 100. I'm getting closer and closer and closer. I'm starting at 2.99, so let's do the table there. Now 2.99 gives me 1.98. 1.982, 1.984, 1.986, 2.994, 1.988. Notice I'm getting closer and closer and closer to my little target value. This is just a nice way of figuring out ordered pairs. 2.999 again for 3. I've got my error. And I've zoomed in on even a little bit closer, and I can keep doing that. I think intuitively you can see there that the value we're going for is 2, the ordered pair. 3 would give me the ordered pair 2 right there. That's the hole in the graph. The y value should be 2. Well, how do we find that value? We've got some numerical methods there that we looked at. We've got some values here that we looked at. How do we actually find the value? How do we find it analytically? We've got an intuitive idea graphically and numerically. Well, if I can factor this thing, and in this particular case I know I can because the fact that I have a hole in the graph, I'm going to have some hindsight there in a moment. If I take this x cubed minus 7x squared plus 17x minus 15 and I can factor it, if I factor it, I'm going to guess that it has a factor of x minus 3. Well, the easiest thing for me to do is to divide it by x minus 3. So I'm going to take a minute. I never learned, what's that stuff called? Symbolic division, synthetic division. I never learned that. I always have to divide it out the long way. So x goes into x squared, x cubed, x squared times. That's x cubed minus 3x squared. Subtract minus 4x squared. X goes into minus 4x squared minus 4x times. Minus 4x squared plus 12. What do I want to do there? I want to 12x. I'm sorry, I want to subtract. I'm going to get 5x minus 15. X goes into 5x plus 5 times. 5x minus 15, 0. So the function that I have right here, x squared, x cubed minus 7x squared plus 17x minus 15, divided by x minus 3, turns out that it will factor, and it'll look like this. My function f of x now looks like x squared minus 4x plus 5 times x minus 3 all over the denominator x minus 3. Now in this particular case it was very nice because my numerator has a factor x minus 3. My denominator has a factor x minus 3. Those will cancel, and an equivalent value is x squared minus 4x plus 5. Now, my question is, when is x squared minus 4x plus 5 the same as my rational expression? And my answer is going to be x squared minus 4x plus 5 is equal to x cubed minus 7x squared plus 17x minus 15 all over x minus 3. Those are equal to each other almost always. Matter of fact, they're equal to each other every time I pick a value for x except for one value. Those are equal unless x is equal to 3. And of course that was my target value. That's the value I'm going for. So this and this is a nice parabola. This is a nice smooth parabola. This is a nice parabola. X cubed divided by x is an x squared, except when we get to that little point 3, we have a hole in it. And that's what this little denominator and that extra factor of x minus 3 do. So these two are going to be exactly the same parabolas except at that point. Well, how do I find what that limit is? Well, the limit is going to come from this value right here. If I substitute a 3 in there, let's say f of 3 is equal to 3 squared minus 4 times 3 plus 5. That's 9 minus 12 plus 5. That's 14 minus 12 is 2. So we can see numerically now how we, one method of finding these things that we can actually say instead of numerically finding an approximation for it, seeing what the target looks like.
Get your mic.
Oops, I'm sorry. Let me fix my mic here for a second. Is that all right? Okay.
Yeah, that's good.
Okay. So we can see that numerically we got a target for it, an intuitive target for it. We kept getting closer and closer and closer to 2, but now we have an analytical way of finding it. So the first technique for finding analytical limits in an analytical way, if you have a 0 in the denominator, is you try to factor the numerator and see if they'll cancel. Let's look at a couple of little examples with that. If we look at f of x equals x squared minus 1 over x plus 1. Now, x squared minus 1, that I chose this one to be very, very nice because that one factors, you know, that's factors into conjugates x plus 1, x minus 1. Well, where does this function mess up? Where does this function have 0 in the denominator? Well, of course, at x equals -1. If x is -1, the denominator is 0. So what I want to do is look at the limit as x approaches -1 of x squared plus 1 over, excuse me, x squared minus 1 over x plus 1. Now, earlier we saw a direct substitution generally works. In this particular case, it doesn't. In this particular case, if you look at it, it gives you 0 over 0. If I substitute -1 into x squared minus 1 in the numerator, I get 0. If I substitute it into -1 plus 1, I get 0. And that's that little indeterminate form. Does this form actually have a value? Is there something I can do to figure it out? So if you end up with 0 over 0, it doesn't mean stop. It means keep on looking. Well, the technique that we've got here is to factor the numerator. X plus 1, x minus 1 over x plus 1. Those will cancel. This function and this function, x minus 1, are basically the same function except at that point. So I'm looking at the limit as x approaches -1 of x minus 1. Now if I put a minus 1 in there, I get a minus 2. Now I've done this whole thing analytically and I don't even know what the graph looks like. So what I want to do is take this same problem and go look at a picture on the calculator and see what this problem's going to look like on the calculator. So turn my calculator on. Let's go to that and I'm going to say x squared minus 1 and I'm going to divide it by, what was that, x plus 1. X plus 1. And I'm going to do a nice zoom 6 and see that that in fact is going to be a line. But it's a line, now see we know this. We already know if we go back and look at the function, we know that this x plus 1 here is going to give us some problem at x equals -1 because it makes the denominator 0. This graph doesn't tell me any information because it makes everything look like a nice continuous smooth curve with no holes in it. So I can do a little magic right there. I did my zoom 4 here. If I choose the right thing on the calculator, I notice there's a little hole in the graph. Well, where is that hole in the graph? Well, numerically, we found it, analytically, we found it a minute ago at x equals -2. If I trace from the right-hand side, now look at the y values. That's what I'm looking for. There's my limit. As x approaches -1, look at my y values. The y values are getting closer and closer and closer to -2. Notice it doesn't reach -2. And if I do my left-hand limit from the left-hand side and get closer and closer from the left-hand side, minus 2.5 here, minus 2.4, minus 2.3, minus 2.2. Again, I'm getting closer and closer to the number that the value, the ordered pair that does not even exist. But again, when we're talking about limits, we don't care if the actual value exists or not. That's not the point. The point is there a target and am I approaching that target? Is that target something that I'm getting closer and closer and closer to? Both from the left-hand side and from the right-hand side. Now, as I look at some particular examples of graphs, I'm going to draw some little freehand graphs here and talk about, does the limit exist? How does the limit exist? So the first one we saw was a nice smooth function like this. And if I have that ordered pair, I think the ordered pair I used a while ago was something like 6, 2. If it's a nice smooth curve, any polynomial is going to work like this. Any simple polynomial, any cubic, fourth degree kind of polynomial. The limit's going to be right there. If I have the example where I have some polynomial with a simple hole in it, then the limit is going to exist. The function is going to be missing there. The value of the function doesn't exist. So what's going to happen is if I come from the left-hand side, I'm going to get close to that point. If I come from the right-hand side, the point doesn't exist, but the limit of that function as x approaches that value does exist. Sometimes you have a nice little, this is called a cusp. Sometimes it's called a kink in the graph, a sawtooth. Sometimes you come up to a little point and then, like a piecewise function, you'll take another function out, one function going in, one function going out. It's sort of a changeover. But nothing, there's no hole in the graph there. There's nothing nasty. So the limit of this function, if the value as I come in from this side, the value as I come in from this side are the same. It's that nice little point up there at the top. So the limit there exists. A bit of a problem comes if you have a limited domain. Let's say you have a domain that starts and stops. So I'm going to look at a domain. Let's say it starts right here and it stops right here. And this ordered pair, let's call this ordered pair maybe 5, 2. So here's my function f of x. My question is, what is the limit of the function f of x as x approaches 5? Well, the problem here, if you go back to the definition, remember the definition says I've got to have a left-hand limit approach that exists, a right-hand limit that exists. I think I did that backwards. A left-hand limit that exists and a right-hand limit that exists. And they've got to be approaching the same value. Well, let's look at the graph. If you look at the graph, I have a nice left-hand limit, but there's even no function over here that is a right-hand limit. I can't come from the right-hand side because the function doesn't even exist over here. So in this particular case, the limit does not exist, but I still have a left-hand limit. I have a left-hand limit, and that's fine. I can still say I have a left-hand limit, but I don't have a total limit because I can't come from the left-hand side and from the right-hand side. So I do have a one-sided limit. A lot of textbooks will call them one-sided limits. But I don't have a complete limit. Another type of function that we look at is a function that has a rational function that has some type of x minus 3 or x plus 4 in the denominator that gives me something that is undefined in the denominator. Now I'm going to do something slightly different for this one. Let's look at f of x is equal to x squared over x plus 1. F of x is x squared over x plus 1. Now we can see, let's leave it like that. X squared over x plus 1. I can already see that there's nothing here that's going to factor and cancel out. So what happens here? What happens with this thing? I know something nasty happens at x equals minus 1. So here's my question. What is the limit as x approaches negative 1 of x squared over x plus 1? I can see here I've got a value in the numerator, but I have that's a non-zero value in the numerator, but I have a 0 in the denominator when I do a direct substitution. So let's go back to the calculator. Let's put this function in the calculator. In the top, I just want a plain x squared, so let's see if I can clean that up. So there's my x squared in the numerator, and there's my x plus 1 in the denominator. And let's do a nice graph of this. Let's see what happens. Now, one of the problems with graphing calculators is they try to make everything functions. And this particular piece right here came up, notice it went down, then it sort of jumped up to here and came up and did that little piece up there. This is actually not part of the graph. This is an attempt on the calculator's part to connect the graph, to make the graph a nice smooth graph. It's not really part of the function that I'm looking at. One way that sometimes you can get rid of that is, in this particular case, I have a, I think it's my mode button. Let me check. Yeah. On my mode button, I can go down to where it says what kind of graph I want. This is a connected graph. If I get a dot graph and I select that, and then I try to graph the function, it gives me the two parts. Now, I need the other one to know that this, it sort of messes up right here. This goes down, this comes down and goes up. I actually have a vertical line in here. You remember these from Algebra 2, they're called asymptotes. There's a vertical line in here that the graph doesn't cross. So let's go back to the overhead and make a little simple, let's see, how does that work? It came down over here, something like that. The graph looks something like that. It had a bottom curve to it, then it had a top curve to it. And what we know, because we know enough about asymptotes, is we know that there's a little magic line in there. Here, the graph is going down to a negative infinity. Here, it's coming from a positive infinity. And this is our -1. Well, let's look at this. What does it mean for a limit to exist? For a limit to exist, the left-hand limit has to exist, the right-hand limit has to exist, and they have to be equal to each other. So if I come in from the left-hand side approaching this -1, what is my graph doing? Well, from the left-hand side, the limit as x approaches -1 from the left-hand side of x squared over x plus 1 looks like it's going to -infinity. It just goes down, that asymptotic line. If I come in from the right-hand side, I can say the limit as x approaches -1 from the right-hand side, coming in from the right-hand side, the graph, the y value, let's say x squared over x plus 1, goes to positive infinity. Well, I've got three problems here. The left-hand limit doesn't exist. It was -infinity. That's not a number. It's not a real number. The limit doesn't exist. From the right-hand side, it went up to positive infinity. That doesn't exist. And even if they did exist, -infinity is not even equal to positive infinity. So in this particular case, with the x plus 1, the factor of x plus 1 in the denominator, the function had no limit at x equals 1, -1. Now, if you go back and look at the graph on the overhead, if you look at the graph on the overhead again. Thank you. Thank you. Any point along here, everything is fine. Everything's hunky-dory. My limit here from the left-hand side and the right-hand side, there's fine. The only place my limits don't exist, the only place the limits don't exist is analytically where the denominator is 0 and my numerator is non-zero. My numerator was non-zero, so I got something like, what did I get, 1 over 0 in there. And that, of course, is undefined. So that gave me a place where the limit did not exist. The limit from the left was not equal to the limit from the right. So we've got a couple of little problems here. Both problems are when the denominator is 0. It helps to look at the graph to see what's going on with the graph. If you have a nice gap between these two things, a jump between that value and that value, you can pretty much look at it and say the limit doesn't exist. A lot of times if you have something, say we had another factor in there that would cancel out, we had a hole in the graph right there. Well, maybe that limit did exist. Notice we've got something, and we're going to be talking about these later, different types of jumps in the graph. We've got a big skip from -infinity to positive infinity, or we've got a single little point skip right here. So we've got two different kinds of holes in the graph that we're accommodating here. What I want to do now is, let's see if I can find a particular graph I've sort of already made. This is a nice little function, okay, on the overhead. This is a nice little function, f of f. It's start f of x. The domain is limited. It goes from -1 to +2. Now, I don't know if you can see this, but from this point right here to this point right here, that's part of the graph I'm looking at. So my domain goes from -1 to +2. My range, my y value, starts at -1, 1. It goes down to 0. We have a hole in the graph. Notice the value of the function is right here. And then after that, it starts out going to this point. It doesn't reach that endpoint. When it gets to where that endpoint should be, it jumps back down to the ordered pair 1, 0, and it continues on as a horizontal line until it gets to 2, 0. So what I want to do is look at the limit of this function at the basic points -1, 0, +1, and +2. So I'm going to be looking at the limit as x approaches -1 of the function f of x. So I'm looking at this point right here. What happens to the graph, what happens to the function as x gets really, really close to -1? Well, I've got a problem here. This is an endpoint I can approach from the right-hand side, but I can't approach from the left-hand side. Remember, we said a while ago, for the limit to exist, it's got to approach from both sides. Physically, it can't. It's not even part of the domain. So the first thing I would say is D in E does not exist. With that in mind, I could say the limit as x approaches -1 from the right-hand side of the function is, I'm writing that sort of small, I know, is equal to 1. It does have a right-hand limit because I can approach it from the right-hand side, but it doesn't have a full limit because I can't approach from the right and from the left. The next thing I want to look at then, after -1, is what happens if I approach 0. So I'm going to say the limit as x approaches 0 of the function f of x. And let's see what happens here. Now here I can approach from both sides. What's happening to the y value as x gets closer and closer and closer to 0 from the left-hand side? The y value is getting closer and closer and closer to 0 from the left-hand side. So my left-hand limit is the y value 0. My right-hand limit, as I come in from the right-hand side getting closer and closer, my ordered pair, my y value, is getting closer and closer and closer to 0. So from the left-hand side and from the right-hand side, I get 0 from both ways. They're equal. So the limit as x approaches 0 of f of x is equal to 0. Let's look at the next one now. The next one, you notice, was a skip. We have a nice little jump here. If I look at the limit as x approaches 1, the limit as x approaches 1 of the function f of x. Now, here from the left-hand side, as the ordered pairs, we're looking at the ordered pairs, as the x value gets closer and closer to 1 from the left-hand side, my y value is getting closer and closer to 1 from the left-hand side. If I come in on my graph from the left-hand side, my y value is 1. If I come in from the right-hand side, what's my y value? If I get closer and closer and closer to the ordered pair 1, my y value from the right-hand side is 0. So my left-hand limit here is 1. My right-hand limit is 0. So my left-hand limit was +1. My right-hand limit is 0. Remember, for the limit to exist, the left-hand and the right-hand limits must be the same. These are not equal to each other, so this does not exist. The limit as x approaches 1 does not exist. From the left-hand side, from the right-hand side, they both exist individually, but they're not equal to each other. This value right here is very much like this one on the other end down here. I have a left-hand limit. Since the function doesn't even exist on the right-hand side, I can say the function does not exist, the limit does not exist, but I can say the limit as x approaches 2 from the left-hand side of f of x is equal to the y value there, 0. Now, one more particular point here, let me say that. Notice right here, the y value, f of 0 here, is equal to 1. The limit, excuse me, on the other page right here, the limit of f of x as x approaches 0 was 0. The actual value f of 0 is equal to 1. These two values do not have to be equal to each other. The limit does not have to be equal to the value of the function. All we have to do for the limit, it doesn't matter whether that point's in there or not. All we have to worry about is what are we getting closer and closer and closer to. So a nice little example of limits there. What I want to do now is to review 3 different techniques for sort of show and tell here. 3 different techniques for analytically finding a limit. One we've already looked at, it's the factor and cancel method. Another one we're going to look at is, the other one we also looked at too, is the substitution substitution form. And another one is a neat little trick for the conjugate form that we're going to be using again later when we look at finding some derivatives. It's going to help us with the definition of derivative. So the first one is the first technique is a simple little substitution. Let's let f of x equal to 5x plus 2. Nice little simple function right here. Let's take the limit as x approaches 5, 5x plus 2. There's nothing, this is a simple polynomial. There's nothing wrong with this little thing. I'm not going to get zeros in the denominator. It's not going to mess up anywhere. So all I have to do is say 5, do a substitution. 5 times 5 is 25, 27. So the first one is just a direct substitution. If I don't get zeros in the denominator, if I don't get something that messes up, this is what I can do. The second one I want to look at is what happens if I do get that 0 in the bottom. So let's let f of x equal to x plus 1 over x. If I take the limit as x approaches 0, that's my tricky point here, of x plus 1 over x, and I do a substitution in there, and I'll get, if I do a direct substitution, I'll get 1 over 0. The indication there is when I graph it, I'm going to have some type of asymptote, so my limit does not exist. But notice my numerator is a non-zero number. Now, as a contrast to that, suppose I have f of x equals, say, x squared minus 4 over x minus 2. And I want to take the limit as x approaches 2 of x squared minus 4 over x minus 2. Now you can already see that factors, but suppose you couldn't see that it factors. If I substitute a 2 into this thing, I'll get 4 minus 4 is 0 in the top, and 2 minus 2 is 0 in the bottom. I get that magic little indeterminate form 0 over 0. That tells me I'm going to have a hole in the graph. Like we saw earlier, well, this is going to be an x squared divided by an x, so it's going to be a straight line with a hole in the graph somewhere. And the hole in the graph is going to be at x equals 2. So the technique here, if I get 0 over 0, what that tells me is somehow or another, my function, the numerator, will factor, and I'll get an x minus 2 in the bottom, and that this value is, this function is the same as this function for all values except x equals 2, but I can use this to find the limit. So now it's just a matter of substituting 2 in here, and my 0 over 0 in this particular case becomes 2 plus 2 is 4. So I have a factor method. A third method is a little bit of an algebra method. It's called the conjugate method. And conjugates, you remember, the difference of two squares, we just saw conjugates, x squared minus 4. The conjugates are x plus 2, x minus 2. And if you remember from the good old FOIL method, multiplying two binomials together, you do first, outside, inside, and last. You do all that little trick. What happens if you have conjugates is the inside is going to be the same numerical value, or the same value as the outside. It's just the signs are going to be different, the same absolute value. This is minus 2x, this is plus 2x. So when we multiply them together, we don't get a middle term. So let's look at the limit of x approaching, as x approaches 0, the square root of 1 plus x minus 1 over x. Now if I substitute a 0 in there, notice 0 in here gives me square root of 1. Square root of 1 minus 1 is 0. And I get a 0 in the denominator also. X is just 0. So I have my magic little, oh, be careful. I got 0 over 0. I don't stop. I keep going. Well, the way I'm going to simplify this is by choosing the conjugate, square root of 1 plus x plus 1. And I'm going to do a little quick algebra here. 1 plus x minus 1 over x. And I'm going to multiply that by 1 plus x plus 1 over the square root of 1 plus x plus 1. And that square root ends before then. What happens is that first term minus 1, first term plus 1. These two are conjugates, and when I do my cross multiplication, it's going to simplify it. Well, I'm going to let you do the cross multiplication. You probably need to do it by hand if you don't follow what I'm doing here, but square root times square root, it would be 1 plus x. That's minus that, that's plus, they drop out, minus 1. And then in the denominator I have x times the square root of 1 plus x plus 1. Now this numerator becomes 1 plus x minus 1. The 1's cancel. I get x over x times the square root of 1 plus x plus 1. Now notice what happened here. Bada bing, bada bang. I got an x here and an x here, and there was a hidden little factor in here that cancels out. Those two cancel. So when those two cancel, I end up with an equivalent statement, 1 in the numerator, the square root of 1 plus x plus 1 in the denominator. So now I can take the limit. You remember the limit was going to 0. So I'm going to say the limit, I'm rewriting it as x approaches 0. But instead of the original function, which was difficult for me because I ended up with 0 over 0, I've got an equivalent form here, 1 over square root of 1 plus x plus 1. Now I can do a direct substitution. I get 1 in the numerator. I get 1, square root of 1 is 1, 1 plus 1 is 2 in the denominator. So I can do an analytic form with that. What I would challenge you to do now that we're coming to the end of the second tape, what I would challenge you to do with this is to look at the algebra again and then actually take this original function, graph it, and see what happens. See, does it actually approach the 1/2? See, is there a hole in the graph? What particular type of graph happens? What I would like to do when we come back then on the next section is to look at what happens to limits, not when you go to a fixed number, like all of our limits. We've been approaching 0, we've been approaching 1, we've been approaching a finite number. What happens when we take a limit and we approach infinity? What happens to a function, for instance, y equals x? It goes off to infinity. A parabola does this. It goes off to infinity in both directions. What happens but maybe to the logarithmic function that comes down and gets closer and closer to the x-axis? We're going to be looking at something called end behavior, and we're going to be looking at something, we're going to be looking at asymptotes. So when we come back for the third tape, we'll continue talking about limits and what happens to limits as they go to infinity. Welcome back to Lesson 1, Tape 3. We're talking about, the course is Refresher Calculus. We're looking at a lot of basic calculus concepts that we haven't seen in a while. And we're saying, oh, yeah, I remember that. I hope there's a lot of that going on. We're looking at continuity. Well, today, this section, we're going to move into continuity. We're going to close up on limits. We're going to look at a few examples of limits. Then we're going to look at what happens with limits as they go to infinity, which includes asymptotes and something we call end behavior. And then after we look at that, we're going to move on to continuity. And after we have limits and continuity down, we're going to look at the definition of a derivative. So if we'll look at a few examples, and I'm going to be using the calculator here. So we're going to be switching back and forth from the written work to the calculator. And I've got some problems written here that I want to look at just as sort of a little problem session here. The function I'm looking at is a cubic function. F of x is x cubed minus x. And I want to ask the question, what is the limit of this function, f of x, as x approaches negative 2? Well, if I'm going to solve it analytically, this is, remember the techniques we were looking at. There are three techniques that we talked about. One is a direct substitution. One is you substitute and get zeros. What can you do with those zeros in the denominator? And the third one was one that we're going to be using a little bit later when we talk about derivatives, was the conjugate form. Well, this one is fairly simple. This is a nice simple polynomial. Analytically, I can get this by just a simple substitution. If I put a -2 in here, I get a -8. If I put a -2 in here, I get a +6. I'm trying to do the arithmetic in my head. A -8 plus 6, that should be a -6. So analytically, I hope that's right. Analytically, I'm going to get the answer as a -6. Let's look at it on the calculator. If we can switch over to the calculator now, the function I'm going to look at, I don't know where that came from, is x cubed minus x, and I'm going to graph that. And x cubed minus x is a standard little cubic equation. Remember when we did our pre-calculus review, it's x cubed, so basically we're going to go from lower left, third quadrant to first quadrant. It's going to be an increasing function for the most part. There's a little change around in here, but basically the whole function is increasing. And I want to look at what happens as x approaches -2. Well, if I do a little bit of tracing and try to get over here close to the -2, I can see my ordered pair somewhere there is about the -2. That's a little bit less, more than -2. That's a little bit less than -2. Remember, if we don't have it actually on the screen, we can do our little zoom 4 and do a trace and actually go to -2. Notice what's happening to the y values here. Oop, off the screen. I can still get them. My cursor went off the screen, but I've still got -2, -6. So back to the overhead. A nice little simple form here, just to do a direct substitution. We reinforced it with the calculator. The next one I want to look at is a little bit different. And I'm looking at this one because when we do derivatives a little bit later, this particular function has a little quirk about it when we do derivatives. It's the absolute value function, the absolute value of x plus 3. If you remember, the linear absolute value functions basically look like a little V shape, and here the problem is going to be the bottom of the V, and that's going to be at x equals -3. Well, this one looks like there's no 0 in the denominator, so this is going to be a direct substitution problem again. Let's put a -3 in here for x, substitute. -3 plus 3 is 0. Absolute value of 0 is 0. So it looks like analytically I can solve that. The limit as x approaches -3 of f of x, in this case, is 0. Let's go back to the calculator. And let's look at the absolute value of x. Now, on my calculator, and I'm sure on most calculators, graphing calculators, I have a catalog feature, which has all of my built-in functions. So I'm going to use my catalog feature here. And my first on the catalog feature is ABS, and that's absolute value. So ABS for absolute value in my calculator, and I'm just going to put in the absolute value of x plus 3. And let's do a nice little graph of that, and we can see the V shape. And of course, we see what happens here at the -3. It goes from the left-hand side, where the y value is going down to 0. From the right-hand side, the y value is going to 0. So the limit from the left is equal to the limit from the right. They both exist, and they're equal to each other. So the limit is, in fact, 0. So graphical reinforcement for our analytical work. Let's go back to the overhead then one more time. And let's make the problem just a little bit sneakier. Up here we looked at the absolute value of x plus 3. Now I want to look at the absolute value of x plus 3 divided by parentheses, in parentheses, x plus 3. Now this one has a little bit of a problem because when I put my -3 in there, I get 0 in the top and 0 in the bottom. So that tells me I'm going to have to do something. a little bit sneaky here. X plus 3 cancels with x plus 3 and leaves a 1, as long as this top value up here, the bottom value down here is positive. If this bottom value down here is negative, this is always positive. I might get a plus 1 or a minus 1. So before I do some substitution into this thing, before I figure out what's going on, I do my minus 3. I get the 0 in the top, the 0 in the bottom. And when I get that form, that indeterminate form that tells me, be careful, see if something's going to factor and cancel. And how is it going to cancel? Well, let's go back to the calculator here. And I'm going to go back to my absolute value of x plus 3. That's the one we just did. And I'm just going to divide it by a plain old x plus 3. It's going to be very nice to get a picture of the calculator here, so the graph here. So let's graph it. Now, I know x plus 3 divided by x plus 3 is 1. That's not a problem. The absolute value is giving me a little bit of a problem. So let's graph it. Oh, that's neat. If you look at it, again, remember we said earlier these functions, these calculators try to connect and make a nice smooth graph. What happens is, numerically, if x is less than negative 3, we get a negative 1. We've got a horizontal line here. If x is positive 3, we get a horizontal line at y equals 1. I'm sorry, I said y equals negative 1 and y equals positive 1. And if we look at, let's see if we can zoom in a little bit on this. We can see to the left of negative 3, this value right here is negative 3. If we see to the left of negative 3, we get a horizontal line at y equals negative 1. To the right, we get a horizontal line at y equals positive 1. So if I come in for the limit, I can see the limit from the left-hand side is negative 1. The limit from the right-hand side is positive 1. Both limits exist, but back to the overhead now. If we go, limit from the left is negative 1, the limit from the right is positive 1. They're not equal to each other, so that particular limit does not exist. The graph, again, was looking like this. Now, what if we had been where this value right here is negative 3? If it had been graphed by hand, it would have looked something like that. We would have had holes in both of these places. The limit here is negative 1. The limit here is positive 1. They're not equal, so the limit of that function as x approaches negative 3 does not exist. So here's one where they factored, but the function did not exist. The next two I want to look at, the last two I want to look at as examples, is this little example right here with the little brackets. That's the notation I learned for greatest integer function. And the function on my calculator that we're going to use is called the INT function. So I want to go back to the calculator and look at this particular function right here. Let me clear that out. I'm going to go to my catalog again. I'm going to hit the I button to get down there and see if I can find INT. There it is, INT. And I want to take the greatest integer of x. Now, if you remember, the greatest integer basically truncates the fractions, throws away anything after the decimal place. It throws off, it takes it down to the lowest integer. So if I do a little zoom 4 on this little thing, I get a little traditional stair step. Again, you've got to remember that we got to be smarter than the calculator. These vertical lines don't really exist. The calculator is just trying to connect the dots. Let me check one thing. Yes, see, I'm still on dot and it's still trying to connect it. Let's see if anything different happens if I try to do the connected, and it's not. It's exactly the same thing. So what's happening now? The limit was at x equals 2. Well, here's 2 right here. That value right there is 2. The limit from the left is 1, but the limit from the right is 2. So in this particular case, the limit from the left and the limit from the right are not equal. So back to the overhead. If the limit from the left and the limit from the right are not equal, the limit does not exist. What's happening with this thing I might have those on the wrong end. I have to think about it for a second. What's happening is anywhere at any fractional value, any non-integer value in here, the limit does exist. But at the integer values, where the integers switch over, none of the limits exist. So that's an interesting little function that has a lot of limits that miss. The limits at any rational number other than, well, or irrational, any real number other than the integer values, the functions, the limit does exist. But at the integer values, the limit does not exist. Okay, the last one I want to look at, f of x equals the square root of x, and this happens for any of the even roots. Let's go back to the calculator. Let's do a y equals square root of x. I don't know what the difference is. I like to take my x and take it to the 0.5 power, to the 1/2 power. Let's do a nice little Zoom 4 graph. And notice the graph started at 0, 0. The graph actually started at 0, 0. We can't take the square root of a negative number. They're complex numbers with imaginary parts. So all of those things out here, the domain, the real domain, doesn't start until 0. So in this particular case, I have a problem where I have a right-hand limit. I just don't have a left-hand limit as I go to 0. So if I go back to the overhead then, the limit as x approaches 0 of f of x, remember from the right-hand side I'm going to 0. From the left-hand side I don't have a graph over here to follow. So the real limit, the total limit, does not exist. That does not mean I cannot say, I mean I can say this, I was using a double negative there, x approaches 0 from the right-hand side of f of x is equal to 0. It does have a right-hand limit, but it doesn't have a left-hand limit. So the total limit does not exist. So a few little review problems of a few little standard example type problems working with limits. Now all of these limits that we've been looking at so far, x has been approaching 2, x has been approaching 0, x has been approaching 3 or 5 or -1. Nice whole numbers. No, well, whole numbers, that's not the point I was trying to make. Nice finite numbers. What happens if you have a function like the exponential function or the inverse function 1 over x? What happens if you have the x and y axis and you have that hyperbola that goes out with what you know as asymptotes? It gets closer and closer and closer to the x-axis. What happens with something like that? Well, let's look at the particular graph. For instance, y equals 1 over x. That's a fairly standard function. To talk about this, I guess I should call it f of x equals 1 over x. And this has some problems. If you graph it, you know it's a hyperbola in the first and third quadrants. It looks something like that. If I look at this limit as x approaches 0 of 1 over x, we saw an example similar to this earlier. If this is my 0, if I'm approaching here, we're going to negative infinity. If I'm approaching from the right-hand side, we're going to positive infinity. That doesn't exist. Does not exist, because the right-hand limit doesn't exist, the left-hand limit doesn't exist. But what I want to look at this is to extend this a little bit and say, not ask what happens as x goes to 0, but what happens as the limit of this function goes to infinity. What happens way out here? And a whole bunch of things can happen in here. I'm not interested in here. I'm interested in what's happening so far out there that no matter how many little wiggles, eventually there's going to be something called end behavior. And this is a fairly little standard example to start off with. What's happening is we're letting x get bigger and bigger and bigger and bigger. Well, what happens to this fraction 1 over x as x gets bigger and bigger and bigger? Well, 1 over 1, 1 over 2. The numerator staying is a unit fraction. The numerator staying 1. 1 over 3, 1 over 4, 1 over 5. X is getting bigger and bigger. What's happening to these fractions 1 over 100, 1 over 100 squared, 1 over 100 to the 100? As the denominator gets bigger and bigger and bigger, the whole fraction is still staying positive, but it's getting smaller and smaller and smaller. So it's getting smaller, but it has a bottom limit. Well, what's happening is, you remember your Algebra 1 or your Algebra 2 teacher back in the 9th, 10th grade something, was saying that we call the x-axis in this case an asymptote, and that our graph is getting closer and closer and closer to the x-axis. Well, the y value on the x-axis is 0. So one of our standard little factoids, if you will, that we're going to be using is the limit of 1 over x as x approaches infinity is 0. Now, depending on what book you look at, some books define it one way, some books say the other way. It's not really equal to 0. It approaches 0. So some books you will see with a little arrow right here, the limit of this thing. Well, the limit is equal to 0, but the value approaches 0. I'm going to use those interchangeably. I don't, as long as we know what we're talking about, I don't think there's that much of a problem with it. The limit is 0, but the value of these fractions are approaching 0. It will never equal to 0. 1 over x will never equal to 0, but the limit will. What happens if we go to 0, if we go to infinity the other way? Suppose we've still got the same graph. Let's redraw the graph here. And let's take the limit as x approaches negative infinity. Now notice I'm putting the negative not on the right-hand side. I'm not talking about a left-hand and a right-hand limit. I'm just talking about a limit going in one direction here of 1 over x. And again, you can see from the graph, if I've drawn the graph correctly, it's getting closer and closer and closer to the x-axis again. So that's also 0. Asymptotic behavior. The x-axis is an asymptote, or we can also call it, a lot of times it is called end behavior. What happens as you go out to the end, either to the positive side or the negative side. So we're going to address a few of those. If you remember, we had a list of properties of limits earlier where we looked at all the different little properties. If you have a constant factor, you can take that out, find the limit, and then bring the constant factor back in and move it. If you're adding two together, if you're adding two functions together, you can take the limits individually and add them together. So if we look at the overhead again, if you remember this sheet from several hours ago on the tape, what I want to do is just change that from a constant value to an infinity. Oh, x approaches infinity, x approaches infinity. And the rule still holds, still with this caveat, not equal to 0. So those aren't going to change any. And I'd like to look at a couple of little examples here. What would we do, for instance, the limit as x approaches infinity of 5 plus 1 over x? Well, I could split that up into the 5, the limit as x approaches infinity of 5, plus the limit as x approaches infinity of 1 over x. Well, the limit of a constant, I don't care how far out you go, the limit of a constant is constant. That we just looked at is 0. So this limit right here would be 5 plus 0 is 5. Now, I don't think you have to write this out every time. I think it's sort of obvious in your, you can do this in your head. But starting out, we probably need to look at a couple of little examples like that. What would we do with the limit as x approaches negative infinity of 4 over x squared? Okay. Well, this particular problem, as x is getting larger and larger and larger, the thing I want to mention here is even though this is negative, it is not infinity, it is still a number, we're just getting larger and larger, well, smaller and smaller and smaller if we're going to the negative side, I guess. If you square it, it still is a positive number, so that's going to be 4 over a very, very large positive number. In this particular case, it doesn't matter because we're still going to go to 0. but in some cases we're going to slip up on this little thing. We're going to have a negative infinity on a square, and that's going to make it a positive. We're going to approach negative infinity, and it's going to make it a positive value. One value that I want to look at is the limit as x approaches infinity of sine x over x. Now this is a neat little, my infinity messed up there. This is a neat little problem because all of a sudden we're throwing, this is one of our first trig functions that we're looking at here. The idea I want to bring out here is sine x. Now we're in radians, so x is a radian value. But what do you know about the domain and the range? Well, the domain you know is all reals. What do you know about the range of the sine function? Well, the range of the sine function, the y values associated with the sine function are -1 is less than or equal to the sine of x is less than or equal to 1. Even if it's the largest value is still going to be the 1, the smallest value is still going to be -1. So this value in here is fairly fixed. It's not a single number, but even if you replace it with 1 always, that's going to be less than 1 over x. This x is still going to go off to infinity. So this thing is going to be like 1 over 0, and 1 over 0 is, excuse me, 1 over infinity. I knew something was wrong there. It's going to go like to 1 over infinity, and that's going to go to r 0. I was using the wrong term. They were using the wrong words there. So sometimes if you have a trig function in here, it'll throw in a little trick like that. Let's look at something associated with in behavior and something associated with limits on the interior, fixed limits, and that would be asymptotes. Sometimes we have vertical asymptotes where the curve will approach. We've seen a few of those. And sometimes we'll have a horizontal asymptote, like 1 over x went down and it approached 0 as it went further and further and further out. How do we find those? How do we tell which are which? And how do we use this concept of limit to work on those particular values? So let's say a horizontal asymptote. A horizontal asymptote, y equals b. If it's horizontal, it's going to be some horizontal value. And the form of those lines is going to be y equals some constant b. Y equals b is a horizontal asymptote if either of two things happen. Now remember, we might be going a horizontal asymptote out to the right, which is positive infinity, or a horizontal asymptote out to the left, which is negative infinity. So we can say a horizontal asymptote exists if either of the following exists. The limit as x approaches positive infinity of the function is equal to b, or the limit as x approaches negative infinity of the function is equal to b. I need to check out what happens to positive infinity, what happens as it goes to negative infinity. Sometimes these are the same, sometimes these are different. So you've got to be careful. You've got to look at the positive infinity and the negative infinity. A vertical asymptote exists if the limit as x approaches a from the left of the function is either equal to plus or minus infinity, or the limit as x approaches a from the right of the function is equal to positive or negative infinity. I need to rewrite again. That's too messy for you to read and try to copy. Let me rewrite that again. Get a better piece of paper. A vertical asymptote exists if either of the following exist, if either of these exist. 1, the limit as x approaches not infinity, but x approaches some finite number from the left of the function is equal to plus or minus infinity. Or if the right-hand limit, this is the left-hand limit, if x approaches some value from the right-hand side of f of x, and we get plus or minus infinity. So, a little compare and contrast. Vertical asymptotes and horizontal asymptotes, they both have to do with infinity. The comparison is horizontal asymptotes, the x approaches infinity and you get a real value. For vertical asymptotes, it's backwards. You're approaching a real value once from the left, once from the right, and you're getting infinity as an answer. So what I would like to do is something I haven't done yet, and I'm going to like to do it because I get to shut up for about 2 or 3 minutes, is I'm going to give you a little problem, and I'm going to give you a couple of minutes to look at it, not too terribly long. If you want to stop the tape and look at it for a minute, a little bit longer than I give you, but I'm going to give you for a minute, about a minute. What I'm going to ask you to do is to look at this particular rational expression and see if you can find the vertical asymptotes and the horizontal asymptotes. So the particular function I'm going to give you looks like this. The function f of x is equal to 3x squared minus 5x plus 2. And the denominator is x squared, 6x squared minus 5x plus 1. So what I'm going to do is give you a minute. You can use your calculator, you can use your algebra, and I want to look at horizontal asymptotes and vertical asymptotes. So let me just sit here for a minute and let you look at that for a second. If you need a few more minutes, you can go ahead and stop the tape and look at this, but I wanted to give you a few minutes to look at it. First of all, to find the vertical asymptotes, we want to find out where the denominator is equal to 0. That's and the numerator is not equal to 0. That's going to give us our non-zero over 0. So the 6x squared minus 5x plus 1 happens to factor, which is really nice. 3x minus 1 and 2x minus 1. So if I want to set that equal to 0 and find out where that is equal to 0, 3x minus 1 is equal to 0, x is 1/3, 2x minus 1 is equal to 0, x is 1/2. So I have 2 vertical asymptotes, or at least 2 potential vertical asymptotes. What might keep one of these from being a vertical asymptote? Well, what might keep one of these from being a vertical asymptote is if this thing factors. If the numerator factors and the factor in the numerator is same as the factor in the denominator, remember from earlier tapes we didn't get an asymptote, we just got a hole in the graph. So I can't just say the vertical asymptotes are here and here. I've got to now look at the numerator, 3x squared minus 5x plus 2. Now, I want to show a little trick here with the calculator. and the 3x squared minus 5x plus 2. It's about evaluating this, because if this is a factor, it'll make the numerator 0, or if this is a factor, it'll make the numerator 0. So what I want to do is look at that, and I'm going to enter that function 3x squared minus 5x plus 2. Now that function right there is function y sub 1. It's the first function here. And if I graph it, there's no reason to graph it, but I can. It's just going to be a nice little parabola, nothing exciting about that. But I want to evaluate it. Well, I have a button called the variables button, vars, short for variable, and I'm going to press that button. I want to go to my variables, all of my y variables for the function, the first entry right there. I'm looking for my y variables for the function, and I'm going to enter that, and I'm going to choose y sub 1, the very first one. So that gives me function y sub 1, and I want to evaluate that at the value 1/3. So I'm just going to do it like functional notation. So I'm going to do just like f of x. This is y sub 1 of 1/3. And if that gives me a 0, then it's going to be a root of the function. Well, it doesn't give me a 0. So let's do it again, and this time I want to put in a 1/2. And that's a 0.25. So neither of those, back to the overhead please, neither of these two particular values right here made the numerator 0. So these are roots of the denominator that are not roots of the numerator. So these two are going to be vertical asymptotes. So both of those are vertical asymptotes. Well, how do you find horizontal asymptotes then? If we find horizontal asymptotes, remember the limit as x approaches infinity of this particular function. So this particular function is 3x squared minus 5x plus 2 over 6x squared minus 5x plus 1. What happens here? If there is a limit, then that limit, if there's a real limit, then this limit is actually a horizontal asymptote. Well, I can't just substitute infinity in there. So there are some little tricks I can do with this. The pre-calculus notation is this. The pre-calculus idea, and we're going to talk about why this works, has to do with the degree of the polynomials in the numerator and denominator. If the degree of the numerator is greater than the degree of the denominator, in this particular case they're the same, but if the degree of the numerator is larger than the degree of the denominator, it'll go off to infinity and it doesn't have an asymptote. If the degree of the numerator is equal to the degree of the denominator, then you take the coefficients, and this is something that's taught in most pre-calculus courses. If the degrees match, you take the ratio of the lead coefficients. In this particular case, it would be 3 over 6, which reduces to 1/2. So this one applies to this particular case right here. I can see that I'm going to have a horizontal asymptote of 1/2. In the case where the degree of the numerator is smaller than the degree of the denominator, then your horizontal asymptote will be equal to y equals 0. This is I'm sorry, that should be y equals 1/2. So these are three things that are taught in a lot of pre-calculus books, is just memorize this particular fact. If the degree of the numerator is greater than the degree of the denominator, then you don't have an asymptote. If the degree of the numerator is equal to the degree of the denominator, then you take the ratio of the lead coefficients. And if the degree of the numerator is less than the degree of the denominator, that means the denominator has a larger degree, so it's getting bigger faster. Your horizontal asymptote is y equals 0. So in this particular case, I found out that I have two vertical asymptotes at x equals 1/3, x equals 1/2, and a horizontal asymptote at y equals 1/2. Well, let's go back to our calculator and check that particular fact out. I need to put some parentheses around this value right here for my numerator, divided by 6x squared minus 5x plus 1. And let's graph that. I'm going to do a zoom forward to get a graph. Oops, I've got something wrong with my syntax. Let's go to and see what's... Oh, I didn't open my parentheses over here. I'm sorry. Now I've got my parentheses opened and closed, so now let's see if we can graph it. Okay. Let me zoom. I'm going to zoom in a little bit. I don't really care what's happening over here for the vertical asymptotes. So let me do a little zoom in. Nope, I zoomed in too much, so let me zoom back out again. Sorry. You can see that it comes over a little bit over the y-axis and it goes up. This is the connection thing. So you can see the two vertical asymptotes. What's more difficult is to see the horizontal asymptote. But if you look at the horizontal asymptote on the thing, you can sort of imagine a nice little horizontal line going below this one and above that one. There's a nice little horizontal line in there, and that's, of course, the line y equals 1/2. So we can use the concept of limit, and one of the things that we're going to be moving to, with the derivative is to be able to take some of these real nasty functions and graph them. So one of the things that we need to be looking for when we do graph these things are horizontal and vertical asymptotes, and we can use limits to find those. Let's see what else I need. Limits, I think that's about all we're going to talk about. Well, that's all the new stuff we're going to talk about limits. We're going to use the concept of limits and talk about something that we know as continuity. Now, continuity is something that pops up a lot of times in calculus theorems. A lot of times it'll say if a function is continuous over an interval. And we all know a basic concept of the function of continuous. The idea of the concept of continuity is that it's a nice smooth curve. If you can draw the curve with no nasty little holes in it, no skips or jumps, if you can put your pencil down and draw the curve and not pick up your pencil point, then the function we can say is continuous. Well, that's a nice intuitive idea. What we want to do is be a little bit more rigorous with this concept of continuity and talk about how does limit, the concept of a limit, work with the concept of continuity, and then we're going to use limit and continuity to talk about what makes a derivative. So the first thing we can talk about, a continuous curve is continuous if it's a nice smooth curve. From this point right here to this point right here, this is a continuous curve. Of course, it stops here, so the curve doesn't exist. This curve that we've seen before is not continuous because when it's nice and smooth here and everything's fine and dandy until I get to that little point, I skip it, and then it's fine and dandy again. So I've got a little problem there. Another problem I have is something like 1 over x, where I have a piece of the curve over here and a piece of the curve over here. So I'm looking at this little function right here is continuous versus these two functions right here that have problems and are discontinuous functions. Well, as a nice rule, smooth curves, polynomials, all polynomials, a nice little thing, all polynomial, no, let me see if I can spell it right, nomial functions are continuous. U-O-U-S. All polynomial functions are continuous. So I'm going to use polynomials a lot to start off with this thing. But what happens with this little polynomial function that's continuous? Well, I want to look at this little point right here. Again, we're talking about continuity at a point. So to draw on a little function I used earlier, that point is 6, that point is 2. This ordered pair right here is 6, 2. And I want to talk about what does continuity mean in terms of limits, and how do limits affect continuity. Well, to be continuous, the first thing I have to do is have a limit at that point. Now, to talk about continuity, the first thing we're going to talk about is a function is continuous at a particular point. So I'm only looking at this point right here. Notice if I come from the left and I come from the right, the limit as x approaches 6 of this function is 2. That's one of those nice little simple things. The limit exists. The limit from the left is 2, the limit from the right is 2, and the limit exists. So the limit is there. I've got that nice limit idea. The other thing that I'm adding for continuity is that f of 6 is equal to 2. The value is there. Remember when we had limits earlier, the target didn't have to be there. I could approach the target from this way, I could approach the target from this way, and the limit was fine. Not a problem at all. Now for continuity, to be continuous at a point, a function has to have that point as a point of the domain. The x has to be a point of the domain, y, the corresponding y has to be a point of the range. So let's give a nice rigorous definition here. Well, not rigorous, but a nice, well, a good enough definition, certainly one that works. And say a function f of x is continuous at point, let's say point A, if the limit as x approaches A of f of x. Now, this in itself goes back to the definition of limit. Remember, for this to even exist, the limit from the left has to be equal to the limit from the right. This is its own little problem to solve. Then I have to say that's equal to f of a. So a function f of x is continuous at a point A. I probably shouldn't have used A twice there, but this is the point A. If the following happens, the limit as x approaches A of f of x is equal to f of a. So I'm going to show you continuity and I'm going to show you discontinuity. The function f of x here is going to be the simple value x. Okay, that's going to be the line y equals x, and I want to choose my point A right here as 1. Well, we know that point is 1, 1. So I want to show that the function y equals x, f of x equals x, is continuous at the point 1. Well, I know that because the limit as x approaches 1 of f of x is equal to, now what's happening here? If I approach from the left-hand side, approach from the right-hand side, the limit is equal to 1. So here I'm doing my limit process. The limit from the left is equal to the limit from the right. They're equal to each other and it's 1. Now the extra thing I have to add in here is that the function, which is x, f of 1 is equal to, well, f of 1 is equal to 1. These two things are equal. The limit of the function is equal to the actual value of the function. And if the limit of the function as it approaches that point is the value of the function at that point, and those two things are equal, then I can say the function is continuous at that point. Well, let's look at a contrasting example, an example that looks very much like this one, but is going to be different just a little bit. F of x is equal to x squared over x. Now, this function right here will simplify to just an x, and that's absolutely fine. And this function is equal to this function. They're equal at every value except when x is 0, because that, remember, that gives us 0 over 0. So let's talk about continuity at 0. Is the function f of x continuous at x equals 0? That's my big question. Well, let's graph it. There's my x and y axis. Now, you can graph it on your calculator if you want to, but what you've got is the line y equals x with a hole right here. And that hole comes from the fact that this thing is the 0 over 0, but it will cancel. So let's look at it. The limit as x approaches 0 of f of x. Let me ask, what is that? Well, if I approach from the left-hand side, I'm getting closer and closer to 0. If I approach from the right-hand side, I'm getting closer and closer to 0. The limit from the left is equal to the limit from the right, so the limit exists and the limit is 0. So that's the first part that I have to find. I have to find, does the limit exist? The second part I have to find is, what is f of 0? Well, in this particular case, f of 0 is, well, if that's my function, f of 0 doesn't exist. So here I have a discrepancy. These two values are not equal. Since those two values are not equal, I'm going to say f of x is not continuous at x equals 0. Now, notice right here, it is continuous at x equals 1. It is continuous at x equals minus 1. It's continuous everywhere on the whole curve except where it had that little hole in the graph, and that's the only place that we have a problem. So it is not continuous there, so we say it is discontinuous at 0. Now, this particular, we'll talk about it a little bit more later. This particular hole in the graph is called a removable discontinuity. It's removable because by moving one point around, by putting one point in there, I can remove the discontinuity. A particular discontinuity like this, where you have, say, 1 over x, and you have that big skip in there, would be called an infinite discontinuity. And sometimes you'll have a discontinuity, I don't know if you remember the absolute value of x plus 3 over x plus 3. You had a jump in the curve from in the graph from here to here that was not finite, and that's called a jump discontinuity. So this one is called a jump discontinuity, and one like this is called an infinite discontinuity. So there are three different basic kinds of discontinuities that we're going to be looking at, and we're going to be naming them as we go through them. Okay, so is a function continuous? Now, this next little thing is it's tricky. It's not tricky if you know what it is, but you got to pay attention to what the question being asked is, because the question can be asked in a way that is tricky. Is a function continuous? Well, basically, what we're saying is a function is continuous if it doesn't have any skips or holes in it. A function can still be continuous. You can still describe it as continuous if it has holes in it, if certain things happen. And it depends on how you're talking about it to be continuous. So this next little thing about 1 over x, it's a little subtle, and you might want to go back. If you didn't understand it the first time, you might want to go back and play the tape again. Because this is it's a little trick about continuity. And the question might be asked subtly, not at all obviously, if you have a question on this, which you probably will sometime. Let's look at f of x equals 1 over x. Now, I know f of x is 1 over x. Looks like I've used it a bunch of times in here. It's my little first and third quadrant hyperbola. And I've got an infinite discontinuity here. So I'm going to ask the question, is f of x continuous? And then I'm going to ask, is f of x continuous? I got that wrong, UOUS, over the real numbers. If I ask just the simple question, is f of x continuous, then I'm implying here that I'm only talking about its domain. I'm only talking about continuity over the domain. And if I talk about continuity over the domain, 0 is not in the domain of that function. So if I'm asking the simple question, is f of x continuous, I get to throw out anything that's not in the domain. 0's in the domain, I get to throw that out. So if 0 gets thrown out, yes, this function is continuous. It's continuous everywhere that it exists. So be careful about that. Now, if I turn around and ask the question, is f of x continuous over the real numbers, all real numbers, that's not the domain. Now I'm including 0, and my answer is no, it is not, because it's got a problem at 0. So when you're talking about just a function being continuous, just straight up continuous, you're talking about, is it continuous on its domain? You're only worried about where it's defined. But a different question, which gives a different answer, is it continuous over all the reals, or it gives you a different set of values to look at, not just the implied domain. So be very careful about that little trick right there. The subtlety of the question is there, and it's not a hard thing to differentiate. You just need to be aware that it's a subtle question, and you have to pay attention to the question. Okay. The last thing I want to talk about on this particular session are the three little things we need to look at. The test for continuity. The test for continuity. It's a threefold test. We've done it. The first thing I want to look at is, I guess I need to write the question, is f of x continuous at x equals some point a? That's my question. Is a function continuous at some point a? Well, the first thing I have to say is f of a exists. F of a has to exist. If f of a doesn't exist, it's probably not in the domain, and it doesn't make sense anyway. So I have to take this value, plug it into the function, and get an answer. The second thing I have to ask is, does the limit as x approach a of f of x exist? This has to exist. So the limit has to exist. As I approach a from the left-hand side and as I approach a from the right-hand side, that little magic target point has to exist. Now this comes back from the last tapes we've been doing on limits. The third thing that I have to worry about is that these two values must be equal. That the limit as x approaches a of f of x is equal to f of a. So it's a threefold step. A typical AP Calculus question might be for them to give you a question and say, is it continuous? And to get full credit for the point, you would have to go through all 3 points. The first point, show that the function exists. The second point, show that the limit as x approaches that value exists. And the third step would be to show that those two values are equal. So that last little screen that we had, the last little writing about the test for continuity, it's a biggie. You need to make your little 3x5 card on that one. I can pretty much guarantee that you're going to be seeing some questions like that again. We'll do a few of those examples when we come back on the next test. What I want to talk about right now, though, is the continuity we've been talking about is continuity at a single point. We're looking at a single point and we're saying we're continuous there. What does it mean to be the whole function to be continuous? We got a whole smooth function. Well, if I have a function that goes from here to here, for instance, and the function is continuous at each point on the interval, we can say the function is continuous on the interval. Our definition of continuity that we looked at and the test only tells us about a point. But if I can show that it is continuous at each point on an interval, then I can say the function is continuous on an interval, on the whole interval. what I would like to do is, let's see if you can zoom in on the overhead just a little bit. Let's see if you can zoom in on this particular section right there. That's a nice little graph that we're going to be looking at. We'll do a couple of little problems right now. And we'll look at, again, this at the beginning of the next tape. The function starts at -1, the domain starts at -1 and goes over here to +3. So I have a limited domain from -1 to +3. I've got a discontinuity here. This is we said earlier, a jump discontinuity. This is another discontinuity. Now I'm just doing this by looking at the graph, a jump discontinuity. This is a removable discontinuity. It's just got a single hole in the graph. And if I can move this point here, I can fill it up and remove the discontinuity. I also am going to talk about continuity at the endpoints. Remember, limits don't exist at the endpoints because you have a one-sided limit but not a two-sided limit because nothing happens over here. But continuity does exist at the endpoint. So we're going to say continuity will exist if either the right-hand or the left-hand limit, whichever one is appropriate, does exist. So this is a graph we're going to start our next class off with. You might want to draw it down and write it down and write a few little notes on it, and then we're going to look at continuity at each of these little points. So we can finish this tape and we'll come back and we'll take continuity, do a few examples with continuity, and move into the definition of a derivative. Welcome back. This is still lesson 1, tape 4. We're going to end up with talking about our continuity issues. What does it mean for a function to be continuous, both at a point and on an interval, and actually at endpoints of a domain. And then we're going to move from continuity to start talking about the definition of a derivative. What does it mean, the whole concept of rate of change, and our first major topic in the calculus. If you can go to the overhead, can you zoom in on that just a little bit? Very good, thank you. We were looking at this particular graph at the end of the last tape, and I said we were going to continue talking about it this tape. So I want to look at, first of all, the endpoints. And when I'm looking at the endpoints, I'm going to be saying a lot of things, and then when we get through talking about this particular graph, we're going to actually write them down. So don't worry about writing everything down now, just sort of follow along with me. Remember, continuity requires 3 things to happen. 1, the limit has to exist. 2, the function has to exist at that point. And 3, those 2 values have to be equal. The limit at the point has to be equal to the value of the function at the point. Well, if I'm looking at this particular point right here, and that's the end of my domain, because my domain for this whole complete function goes from -1 to +3, then we have already said that point right there doesn't have a limit. It doesn't have a limit because it does have a right side limit, a limit from the right hand side, but it doesn't have a limit from the left hand side. So we cannot say the limit exists. Well, there's a little special case here. A special case about continuity. At an endpoint of a domain, now be careful, it doesn't mean this point right here because this isn't the endpoint of a domain. That's on the interior of a domain. The domain goes from -1 to 3, so we're only looking at the starting point and the ending point if they exist. We're not looking at an interior point. Then you only have to consider either a right-hand limit right here or a left-hand limit here for the continuity to be true. So for this particular point right here on the left, even though there isn't a complete limit, there's only a right-hand limit because I can only come in from the right-hand side, I can still say the value of the function, because at -1 the value of the function is 2, is equal to the right-hand limit of the function, which is 2. So we can say it is continuous at that endpoint. Now that's it's a little change. The limit doesn't exist, but the right-hand limit does. And since the right-hand limit exists at the end of the domain, then we can say the function is continuous. The same thing is true over here for this point right here. There isn't a right-hand limit, there's only a left-hand limit. And since this left-hand limit exists, we can say the function is continuous at that endpoint, since the value of the limit is equal to the value of the function at that point. So we have continuity at this endpoint, and we have continuity at this endpoint. Now let's look at some points on the interval from -1 to 3, in particular the point 0, x equals 0, x equals 1, and x equals 2. Here at x equals 0, graphically you can see that there's a skip. Analytically, what we see is, remember, the limit has to exist. Well, the limit from the left is 1. The limit from the right is -1. The limit from the left does not equal the limit from the right, so the limit doesn't exist. Well, if the limit doesn't exist, the function cannot be continuous at that point, at the point x equals 0. The same thing is happening here with different numbers. The limit from the left is 0. I'm going up to 0. The limit from the right, notice this value doesn't exist. It exists down here. It doesn't exist up here. But the limit from the right is still a +1. So the limit from the right is +1. The limit from the left going into 1 this way is 0. 1 doesn't equal to 0. So this particular point, x equals 1, is not continuous. We're not continuous at x equals 1. These two are sort of similar in their reasons for not being continuous. This one has a little different reason for not being continuous right here. Here the problem is the limit from the left is equal to the limit from the right. The limit from the left is 0. The limit from the right is 0, because both of these values are going into 0. So the limit, I'm going to write that as the limit as x approaches 2 of f of x is equal to 0. So the limit from the left is equal to the limit from the right, and the limits exist, and I'm happy. That's excellent. I've got a limit at that point. But remember, for the definition of continuity, the next thing you have to have is f of 2. The function has to be defined at the point that we're looking at. Well, here the problem is f of 2 is right here. The point in the function is right here. So 2, 1, f of 2 is equal to 1. So remember my three conditions. Remember the three conditions for continuity. The function has to exist at the point. The limit as x approaches that point of the function has to exist. And the big thing, these two values must be equal. Well, those two values are not equal, so I can call this point right here, I can say this is a point of discontinuity. The function is not continuous at that point. Now, we have different names for these two types of continuity. For this particular type of continuity right here, where there's a big skip between the left-hand point and the right-hand point, we call that a jump discontinuity. So I'm going to call that, I'm going to write J-U-M-P, because we have to jump from this point to this point to make it continuous. It's an interval. It's a whole interval. It's not a single point. Whereas, in contrast, this point right here, there is only one point out of place. And if I'm using the word that's chosen here, remove this point and put it down here, replace that single point, then it would be continuous. So we're going to call this a removable discontinuity. Now, if you reflect back on graphing, both of these particular points are of the fraction something over 0 form. This one is like maybe a 5 over 0, undefined, but this point right here in the graph would end up being like a 0 over 0, and we can remove that single point. We have a hole in the graph. So there's an analogy between this and the things we've been looking at earlier. So as a nice little review of some issues of continuity, this graph shows two of them. There is one more. general way of looking at a discontinuity, of defining or naming a discontinuity. And that would be something like the graph of y equals 1 over x again. We've used that one quite a bit. It's a nice little function. It's a nice hyperbola, looking like that. And let's look at the continuity at x equals 0. Now, as a reminder, as a refresher, well, that's not drawn very well. That should look a little more asymptotic. Remember, 0 is not in the domain. Since 0 is not in the domain, I can say this function is continuous because it's continuous everywhere else. But if I look for continuity at 0 in particular, then what I have to have is the limit as x approaches 0 of the function 1 over x has to have a value. Well, it doesn't. That goes down to negative infinity. That goes up to positive infinity. This does not exist. The value of the function doesn't exist. But if you look at the skip I have to make, this goes down to negative infinity. This goes up to positive infinity. We would call this an infinite discontinuity. I'm going to abbreviate that. I don't have enough room to fill it out. We'll call this an infinite discontinuity. So there are three types of discontinuities that we've talked about. The removable discontinuity that just has the one little hole that you can plug in. You can remove the point and plug it in and fix it up. A jump discontinuity, which is a finite distance, and then an infinite discontinuity, where to connect the 2 points, you would connect the point down here and the point up here. You would need an infinite line segment. So, with those ideas about continuity, I want to look at a few little problems associated with discontinuity and continuity, and I want to give some examples. The first example is polynomials. Polynomials are continuous. Y equals x squared, y equals x cubed, all combinations of sums of the power series. All polynomials are going to be continuous. They're nice smooth curves. They have no holes in them. Everything is hunky-dory. We don't have any problems with them. Polynomials are continuous. We looked at y equals 1 over x, sometimes called the inverse function, sometimes written as x to the minus 1. Now remember, this is, I keep hitting on this, but this is the tricky one. It is continuous if you say it is continuous over its domain. But it is discontinuous if we ask about continuity over the reals, because it is discontinuous at x equals 0. Well, this is a sort of a basic example of all rational functions, where a rational function is a ratio of polynomials, something like f of x is equal to 2x plus 1 over x minus 4. This is a rational expression. This is a rational expression, a little bit more general. Rational expressions are continuous on their domain. But remember, for this thing right here, the domain is all real numbers except 4. But it is discontinuous. So it's going to be discontinuous where it has in this particular case, has a vertical asymptote. It can also be discontinuous, x squared minus 16 over x minus 4. It can also be discontinuous at x equals 4 for a different reason. Now, these are two different kinds of discontinuities. I can look at this one and tell that this is, has an asymptote at x equals 4, and this one has a hole in the graph at x equals 4. I can tell that because, remember, if I take this thing and factor into the difference of two squares, it'll reduce to x plus 4. So, both rational expressions, two different little variations on how you get discontinuities. This one would be either a jump or an infinite discontinuity. This one would be a single point missing, which would be a removable discontinuity. Absolute value function, y is equal to the absolute value of x. Continuous, no holes in it. Really nice. Now I've used this a couple of times to sort of keep it in your mind. We're going to be looking at something about the derivative in a little bit, and we're going to be using this function. So I'm using this now so that in a little bit we can do a little compare and contrast and come back and remember this one. Y is equal to the greatest integer x. Now remember, that's the one that's the little step function. And we said that's going to be continuous at all the whole numbers, discontinuous at all the whole numbers, all the integers, but continuous everywhere else. Exponential, standard exponential function looks something like this. Remember, for instance, y equals 2 to the x. It goes through the ordered pairs 0, 1, and it's an increasing function. Exponential functions are asymptotic here. They go off to infinity this way. Exponential functions of this form are continuous, nice smooth curves. Similarly, their inverses, logarithmic functions. For instance, y is equal to the natural log of x would look something like this. Always increasing. Now, remember, for the natural log functions, the domain 0 and below is not part of the domain. The domain here is x has to be greater than 0. So everywhere greater than 0, this function is a continuous function. Another one would be associated with your trig functions. Now, trig functions, you're thinking to yourself, oh, sine, that's nice and smooth. Cosine, that's nice and smooth. We got the little sinusoidal curves doing the up and down thing. And then all of a sudden you think about the the tangent and the cosecant and the secant and all those little asymptotes. Well, remember 1 over x. Remember, when we talk about 1 over x, when we talk about continuity, we talk about it on its domain. So the sine and the cosine function, if we look at the sine function and the cosine function, those things, they keep on going. Not a problem with understanding how they're going to be continuous. The tangent function, remember, has the little asymptotes. The tangent function is going to be continuous even though you have a skip like this, because this point right here and this point right here, for the tangent functions are not part of the domain. If we ask about the continuity over the reals, it is not continuous, but continuity over its domain, it is. I would like to work then a few particular examples and talk about continuity and discontinuity. So the first one would be f of x is equal to x plus 1 over x times x minus 1. Now, nothing cancels out here, so we're going back to our asymptotes, what our concept of asymptotes are. X plus 1, x minus 1. What are we going to do with this? Well, the key points I'm looking at are going to be 0 and 1, because 0 makes the denominator 0 right here. 0 makes the denominator 0 for that term right there. So what can I say about continuity at 0 and continuity at 1? Is it a continuous function? Well, obviously you know it's not. Obviously you know it's not. Let's go over to the calculator, though, and talk about what we can do with the calculator. Let's clear that out. Let's go to the function that we're looking at. It was x plus 1 divided by x times x plus 1. Let's see if I've got my parentheses correct. Okay. And let's zoom 6 that thing and see what happens. Let me go back to this thing and make sure I put it in there right. I have x plus 1. I have x. X minus 1, I'm sorry. Now let's graph it and see what happens. There we go. We see some nice little interesting stuff right here. Let's see what happens if we zoom in to get a little bit better picture. I see I have a vertical asymptote here. Now remember, if you have a vertical line, we talked about this earlier, the calculator itself tries to turn this thing into a continuous function, tries to connect the dots. But we can see that we have a discontinuity both at 0, well, we can see the indication of it right here. It goes up, it looks like it's going to be asymptotic to the line x equals 0 here, and then we have the calculator sort of drawing our little asymptote here at x equals 1. So we've got nice little graphical, oh, I don't know what the word would be. It's backing us up. What we're saying, what we're figuring out analytically here by looking at that thing, the calculator is backing us up. Let me look at one more particular function. F of x is equal to x squared minus 1 over x minus 1, where x is not equal to 1. Obviously, x is not equal to 1. If I say x is not equal to 1 as part of the domain, then this function is continuous. If I leave this out, and I can't leave that out. If I say, what is this over the real numbers, then it's going to be discontinuous at x equals 1. But let's look at the graph of this particular thing. F of x is equal to x plus 1, x minus 1, over x minus 1, cancel, cancel. These two things are equal. I guess I should call this S sub 1. These two things are equal as long as we leave out that particular single point x equals 1. So the line x equals 1 is going to look like a straight line, y equals x plus 1. It goes right here. It has a slope of 1. Now that's the line y equals x plus 1. But that's not this function, because this function has a hole in it when it gets to 1 right there. So the function I'm looking at actually has a hole in it when I get to that little point right there. And we've seen enough of these examples to know that that's going to happen. So what I want to ask now is a question that is pretty much a standard question that's asked in a lot of calculus, is what can I do to that function to plug in that hole? What can I do to that function to define a point so that my function does become continuous? So what I've got to do is find out what that hole is that's missing, and I'm going to use the concept of limit to do that. I'm going to use my definition of limit to find out what's missing, and then I'm going to make it a piecewise function. So let's go back and let's look at this particular thing right here. The limit as x approaches 1, that's where my problem point is, of x plus 1 is equal to 2. So that ordered pair right there that's missing, the hole in the graph that's missing, is the ordered pair 1, 2. Now my original function was this. F of x is equal to x squared minus 1 over x minus 1. If that's my original function, that's as long as x is not equal to 1. Well, I'm going to turn it into a piecewise function. And the way I'm going to turn it into a piecewise function is have two different pieces. The point I needed to fill in was 2. So if I have f of x is 2 when x is equal to 1, then this little component right here plugs in the hole, and I'm a nice, happy, continuous function everywhere. So what a very typical question that's asked in a lot of textbooks, a lot of homework assignments, things like that, is if you have a function with a removable discontinuity, with a hole in the graph, how can I fill in that hole in the graph? What can I do to make the whole function continuous? And this is an example of the way to do that. You find the hole that's missing, and then you make a piecewise function out of it. This is good for everywhere except x is equal to 1. This is what you need to fill in the missing hole. There are several little theorems on continuity that are pretty powerful theorems. And one of them you actually use in a lot of the a lot of Algebra 2, Algebra 3 pre-calculus courses. that you use them. Excuse me. And the first theorem, let's write it down. The first theorem that says, if a function is continuous on a closed interval. Now remember, closed interval means it contains its endpoints. If it contains its endpoints and everything's nice and happy, we saw that example earlier, we are continuous at the endpoints also. Then it follows, if this is true, the following things are going to happen. Excuse me. The function contains a maximum and a minimum value on the interval. That means if a function is continuous, now remember, if you want to go back to the smooth curve thing, you can write it without picking up your pencil. You don't have a part over here and a part over here. If it's continuous on a closed interval, then we're guaranteed that the function will contain a maximum point and a minimal point somewhere on that interval. This is a lot of time called the extreme value theorem. Extreme meaning either the highest or the lowest. So as an example, if I have a continuous function that starts at A and ends at B, what it says, if I start at A and end at B, and it's a closed, so I have to include, remember, closed interval, I have to include my endpoints, then somewhere between A and B will be a maximum point, and somewhere between A and B will be a minimum point. Now, on this particular graph, it looks like my maximum point is right there and my minimum point is right there. I could have gone down below the axis and back up. I just happen to be staying above the x-axis on this. The function contains a max and a minimum. Now, be very careful. If I have a constant function, for instance, f of x equals 2, and I go up 2, and I want to look at it maybe between 1 and 5, and I have a constant function, I still have a maximum value and I still have a minimum value. My maximum value is 2 and my minimum value is 2. But on this interval, I do have a maximum value and a minimum value. They just happen to be the same value. I've got problems if my function is not continuous. So let's look at the counterexample. Let's look at what happens if my function is not continuous on this. If it's not continuous from A to B, I might go up, have an asymptote, and then come back down. And the graph might look something like this. There's my A. I'm closed. I include A. I include B. I go up to infinity. I come down from infinity. I have a minimum value, whichever one is smaller, A or B, but I don't have a maximum value. But I can't expect to have a maximum value because my function is not continuous. I have this discontinuity in here. Another little problem is this. Suppose the function is not on a closed interval, not defined on the closed interval. Here I violated the continuity. Here I'm violating the closed interval. I have a minimum value on this particular function. The minimum value, if this function is f of x, the minimum value is f of a. The lowest value here. What is the highest value? Well, if it's not closed, that means b gives me f of b. F of b is not in the function. So what's the highest value? Well, now we're asking, what is the biggest point? What is the largest point that is less than this y value right here, which is the function evaluated at b? Let's give it a number. Let's call it 5. What is the largest value that is less than 5? What's the largest number smaller than 5? And the answer is there isn't one. Anytime you name one, 4.9, I can say 4.99. You say 4.99, I can say 4.999. That's a property of the real numbers known as density. Between any two real numbers, you can find another real number. So I've got two violations here where I don't have max and min values, but that's because I violated the conditions. One, the function has to be continuous. Two, the function has to be on a closed interval. So that's our first little theorem, extreme value theorem, that guarantees that if a function is continuous on a closed interval, that somewhere on that interval I'm going to have a biggest point and somewhere I'm going to have a smallest point, a value where y is largest and a value where the y is the smallest. Now, as a little caveat there, warning here, be careful. But both of these, if say this hump went up exactly this high, both of those would be maximum values and they'd just be equal to each other. But so I guess what we're really saying is not there's one value, but there is at least one value that is larger than every other value. There might be a tie. It's okay to have a tie for max or min. Okay. Another theorem is one that you use quite a bit in when you find roots for polynomials in pre-calculus classes, and that's called the intermediate value theorem, which is a theorem about a value between two things. So we've got the same condition. If a function is continuous on a closed interval, again, continuous, no holes, no skips, no jumps, on a closed interval, we start at A, we end at B, and we include A and B. Then for the intermediate value theorem, I'm going to say, I'm going to start here at A, and I'm going to go here to B, and my function is going to look like that. It goes on a closed interval. I include A, I include B. The smallest value is, or at least the value here is f of A. This value here is f of B. Now, f of A in this case happens to be the smallest value. F of B doesn't have to be the largest value. As a matter of fact, if I change the graph and make this go up high, f of B is not the largest value. The maximum value is over here. So in this case, f of A just happens to be the smallest. It doesn't have to be. But what the intermediate value theorem says is if you look at the starting point and the stopping point and you take every value in here, and I'm going to call an arbitrary value in here m for middle, then I'm going to say if the function is continuous on a closed interval and if m is a number such that f of A, my starting point, is less than or equal to m, is less than or equal to f of B, my stopping point. Now, I might even go higher and lower in here, but I'm only looking at the points between here and here. Then I can guarantee that somewhere then C, where C is between A and B, I'm going to be able to find a C that gives me every value in here. Then there's at least one number C such that, this is my little symbol for such that, it's a backwards epsilon with a colon. I don't know where I picked that up, but I've used it for years. Such that f of C is equal to m. That means if I start here and I stop here, then I'm going to be able to find an ordered pair for an x value for every y value between there. Every y value between there is going to have an x value that will yield it. Now, where have you used this before? Well, the place most people have used this before is finding roots of polynomials. If you have a polynomial that has a root right here, and that value is 1 and that value is 2. Well, the ordered pair for 1, I'm going to just call it minus 1, minus 1. And I'm going to call this, just to make the numbers easy, the ordered pair 2, 1. let's say we have a function here. Then I'm only interested on this piece of the function right here, and I have a closed interval. That is, it's a polynomial, so it must be continuous. So I'm only looking for at this piece right here. Now my starting point starts at minus 1 on the y-axis, and my stopping point ends at 1 on the axis. So if I choose any value in here, if I choose any value between -1 and +1, then I can find something, an x value between 1 and 2 that'll give me the y value between -1 and +1. Well, what y value am I interested in? Bingo! That's the y value I'm looking at right there. The x value that gives me a y value of 0. And the intermediate value theorem guarantees that I can find that. If the function is continuous and closed, then I can find a c. Now, be careful. There may be more than one value of c. It just guarantees that I can find one value. I might be able to find an infinite number of values, or certainly more than one. So I'm not required just to find one, but I'm guaranteed there will be at least one value. In that case, that means there is a root to the polynomial. So anytime you go from negative to positive on a polynomial, or anytime vice versa you go from positive to negative, you do the same thing. Between this value and this value, there's an x value that will give you the y value of 0, the intermediate value theorem. And you use that all the time in pre-calculus classes, or like in Algebra 2 and Algebra 3 classes, looking for roots of polynomials. Then you do things like you bracket it in, you get closer and closer and closer, and you can narrow that down a lot easier by making this interval smaller and smaller and smaller. Okay. Continuity. That's a good bit about continuity. The next thing we want to do is turn from continuity to the concept of rate of change, and we're sort of going into our derivative here. What is a derivative? And for derivative, we're going to need to look at continuity, and we're going to need to look at limits. So it's important for us to have an understanding, at least a good intuitive understanding of limits and continuity before we look at derivatives. Now, you could probably talk about calculus several different ways. Some people have said calculus is a study of what happens when you divide 0 by 0. Other people have said calculus is the relationship between speed and area, and how can you figure out how speed and area are related? Well, if you remember your calculus, speed is the derivative. Speed is velocity, which is the derivative of distance, and area under the curve is the integral. So what we're going to do is start talking about the derivative, and we're going to talk about it as something called another way of talking about calculus, and that's the rate of change. Now, again, one of the problems Newton had when he came up with this stuff, I don't know, middle of the 1600s, maybe about 1650, 1660, whenever it was. He looked at this and he had little things called infinitesimals. And he was trying to look at what happened at an infinitely small piece. Well, that whole thing is some sort of an artifice at best. It's a nice way to make an answer, but I'm not sure I'm not convinced that whole thing really in actuality exists, but it's a nice way of thinking about it, and that's what we're going to look at. We're going to look at what happens at a point. If I walk from here to the store and buy something, I can figure out what my average speed is. Take my total distance, divide it by my total time. That doesn't mean I'm going the same speed. If I drive from one town to another town, I might drive slowly at the beginning, get on the interstate, drive very fast, and then have to slow down a little bit. So I'm not going a constant rate of speed, but I got an average speed that would be equivalent if I went that same speed the whole distance. So for over a time limit, we have that good old-fashioned formula D equals RT. That's something we learned back in the grade 4, grade 5. Distance is equal to rate times the time, and that was really our first hint that something was going to come up with calculus. We didn't know it yet, and thank goodness they didn't tell us. what we want to do then is to take that time interval that we're traveling, and we want to make that time limit shorter and shorter and shorter and shorter. So what I want to do is make a few little pictures here and talk about rate of change. Okay. I always have trouble drawing these because when I make my curve, I don't make it curvy enough to draw the lines I like, and then if I make it curvy enough, I end up making it not a function by pulling it back around. So we're just going to have to deal with what I can do here. This is a little point A. This is a little point B. And I'm going to call this x-axis time. So I'm going to start at time A, and I'm going to go to time B. And this represents my motion. Excuse me just a second. Now, this point right here is f of A, and this point right here is f of B. And from time A to time B, I have moved from point f of A, position point f of A, to a position up here, point f of B. I can find an average by doing something that we learned maybe in pre-algebra, maybe in Algebra 1, and that's something associated with the concept of slope. If I wanted an average rate of change, now look at what's happening here. I'm moving fairly slowly and I'm not increasing. Then as I go along, I'm increasing faster and faster and faster and faster and faster, and I'm going pretty fast right here at the end. I'm speeding up towards the end. I'm getting faster and faster. I don't have a steady rate. To get a steady rate, I can connect these 2 points with a straight line. Notice I'm going from A to B. I'm covering the same distance, and my increase is pretty steady. Well, slope tells me the rate of change of a straight line. Now, how do we compute slope? Well, slope is rise over run, change in y over change in x, or I'm going to write a particular fraction here. I'm going to subtract the y values in the top. So I'm going to say f of b minus f of a. And in the bottom, I'm going to subtract the corresponding x values, b minus a. So for a straight line, this goes back to our good old Algebra 1 definition of slope. This little thing right here is called a difference quotient. Difference quotient for obvious reasons. I'm taking a difference here, you subtract, that's a difference. It's a difference here. And my quotient is the fact that I'm dividing the numerator by the denominator. So it's a difference quotient. And if I wanted to find my average rate of change between this point and this point, then all I would have to do is know that ordered pair, substitute them in here, and get the slope of the straight line. I'm going to call this straight line, I'm going to call it the secant line. If you remember from your geometry, a secant is a line that crosses, in your Euclidean geometry, we defined a secant as a line that crosses a circle in 2 places. Well, it's not a circle here, it's a curve, but it's crossing the curve in 2 places, so here and here I'm going to call that the secant. So the average rate of change is the slope of the secant line. If I start here and end here over that time limit, I've got a good steady rate, I could go there. But that's not what I did. I increased a little bit here at the beginning, and then I got to some little point over here, and notice I'm starting to get steeper and steeper and steeper and steeper and steeper and steeper. So I'm changing the rate at which I am getting towards this point. It was not a good steady rate. This tells me what I could have done as a steady rate, but it doesn't tell me what I actually did. So what we're going to look at is what I actually did. And not only what I actually did, but what I was actually doing at each individual point. So let's look at the same graph again. A, B, f of A, f of B. And let's say the slope of the secant line, the straight line connecting AF of A, BF of B, which is the slope of the secant line. I'm going to call that my average rate of change. And for many, many things, those two are equivalent. For many, many concepts, the average rate of change is good enough. But suppose I don't want to find out what I did from A to B. Suppose I wanted to find out what I did from A to C and then from C to B. Suppose I wanted to break it up into two little parts right here. Well, I'm going to call that f of c right there. Well, look what happens at f of c. A goes to C, and then C goes to B. Notice I'm ending up at the same point, but the first half of the trip, notice if you remember, the slopes are positive here, but the slope is less steep. My average rate of change here is slower, or it's less than my average rate of change here. Slower was not a good word. It's less. This might be a slope of about 1, whereas this might be a slope of 2 or 3. So for over the whole trip, I've got a slope right here that I could say I didn't really go that fast here, but I sped up the second half to make up for the slowness in the first half. So what have we got here? Instead of an average rate of change here, I've got two little average rates of change. Well, let's do another point D in here. And I'm going to call that f of d. Possibly, it's going to be hard to see this, I can do f to d, then d to c, then c to b. And I've got, let me draw it like this, I've got slopes that look like that. These are parallel to the actual slopes. It was sort of hard to draw that in there. I've got a really slow increase, a little bit bigger increase, and then to finish out I've got a bigger increase. Well, what I'm really doing is I'm taking this point and I'm moving it like a limit. I'm moving it in from the right-hand side till it gets closer and closer and closer and closer to A. It went from f of b up here down to f of c. It went from f of c to f of d. Then it went from, if it's going from f of d, going down to f of a. Well, what's going to happen? The big slope is over that time limit. The next slope here was over that time limit. The next little interval we looked at was over that time limit. What's going to happen if this point moves in closer and closer and closer and closer? Well, as long as it doesn't reach there, I'll be able to still find all those little slopes because I'll have my f of b minus f of a won't be the same number. And even if it is, it doesn't matter because in the denominator, the right-hand number minus the left-hand number won't be the same. And as long as I keep 0 out of the denominator, I'm happy. Analytically, I don't want a 0. So what can I do with that? Well, next time I do this, I'm going to have a bunch of these already drawn up. There's my first line over that whole interval. If I look at that, this is my nice little secant line here. If I look at that, this point as it moves, as this point right here, the point where we intersect right here, moves closer and closer to my f of a point down here. It's getting, in this particular case, it's getting flatter and flatter. The secant line is getting flatter and flatter. It's almost approaching actually a horizontal line. In this particular case, it doesn't always approach a horizontal line. What happens if this point, as this point right here that we're crossing over on the right-hand side, gets closer and closer and closer and closer in here? Well, what's happening is the distance between this point and this point, let's see if I can make that little line. The straight line between this point and this point is getting smaller and smaller and smaller. And the f of b minus f of a in the numerator is not a problem because I can have the numerator as a 0. But in the denominator, my b minus a is getting smaller and smaller and smaller. And that's a problem because if it gets small enough, this thing can be equal to 0. And if it's equal to 0, then I've got some of those issues that I was looking back at about continuity. What happens when the denominator is 0? So that's what we want to look at. We want to look at a situation where we can take a bunch of secant lines like this and divide that thing up into a bunch of different smaller trips until this point right here that moves to here, that moves to here, that moves to here, 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 actually approaches A. And it gets so close I can't tell it, the difference between B and A. So what I want to do is let B get really, really, really close to A. So close that it might as well be 0. And if we do that, then all I'm going to do is take, analytically, to talk about this, all I'm going to do is take the difference quotient, which is f of B minus f of A, over B minus A. And I want to take the limit of this as B approaches A. Now, this is written in terms of A's and B's, and I'm not really sure if this is this is perfectly correct. What we're doing, we're letting B get closer and closer to A. But in a more general term, if this is f of x, I'm going to change it around a little bit. Instead of calling this B, I'm going to call this interval in here h, and I'm going to call this point A plus h. A is right here. That distance is h, so that point is A plus h. I've just added a little bit to A. This point is f of A. This point up here is f of A plus h. And now I'm going to rewrite this formula in this notation, and I'm going to say the limit as f of A plus h minus f of A over A plus h minus A. And I want to take the limit. Now, what's changing here? Here, on this last one, I was actually moving B closer and closer and closer to A. I was moving B closer and closer and closer to A, so B was approaching A. That's not a problem. Now, I'm not letting B still approaching A, but what's changing here? I don't have a B. What's happening is the point moves here. The h value I'm talking about, what I'm adding to A to get this difference in here, this h value is getting smaller and smaller. And the h value is basically going to approach 0. Now, I'm going to make one more generalization of this. I have a specific point right here, A. I can let A doesn't have to be a fixed point. A can be any general point, so I'm going to replace A with the sort of a generic variable x. A is generally thought of as a fixed point, x is a variable, so I'm going to rewrite this as the limit as h approaches 0 of f of x plus h minus f of x over, now if I look at this, x plus h minus x, what's going to happen up here? The two x's are going to subtract, and all I have is a h. So this is a limit. It's a limit, and you know what does it mean for a limit to exist? You have to have the limit from the right equal the limit from the left, so we've got a limiting problem here. And this is our difference quotient that comes from the slope. And this is our definition of a derivative. This is how we are going to find a derivative. The derivative of a function is the limit as h approaches 0 of f of x plus h minus f of x over h. And it tells me rate of change not over an interval, but as h gets really, really close, we are finding it at a particular point. And we're no longer going to have a secant line, but we will see in the next section how we're going to end up with something we call a tangent line. Okay. So, let's see. That's talking about rates of change and talking about the definition of a derivative. We're going to work a little bit more with that. And let me see what we're doing in the next, in tangent lines. Well, of course, that makes sense. So that's the end of tape 4. Tape 5, we're going to talk a little bit more about tangent lines, and we'll see you shortly. Welcome back. I think you should be getting pretty proud of me. It's been about 2 lessons now since I stepped on my little wire and pulled my microphone off, and I'm starting to look at the camera instead of looking at the TV set over here. So you ought to be pretty proud of me. What we're going to be doing today, this lesson, is we're going to be looking again at average rate of change and turning that into a derivative and looking at working some problems using the definition of a derivative. The derivative we started talking about as rates of change, and we were looking at, last class we were sort of looking at the idea of a secant line and a secant line moving, a secant line being an average rate of change over an interval. And what we want to do today is turn that average rate of change into an instantaneous rate of change at a particular point rather than over a particular time interval. So if we'll look at the overhead, what we want to do is look at an average rate of change. I mean, that's, and that we looked at that as maybe the slope, if you'll remember the formula for the slope that we looked at yesterday. If I have a particular function that starts at point A and does a lot of stuff to get to point B, if this is point A and this is point B, I can see that a lot of stuff went on in here. But if I want to find out the average thing that went on, just make it a nice smooth curve, nothing fancy about it, then what I want to do is draw a direct line segment from the starting point at A, f of A, to the stopping point at B, f of B, and find the slope of that line. And although different things happened along the way, I sped up, I slowed down, I went fast, I went slow. Here I really went slow and I had to speed up a lot at the end to catch up. If I had gone this average speed over the whole distance, if I had gone this nice steady speed right here, I would have achieved the same results. So that's what we mean by an average rate of change. An average rate of change is an average over an interval on the x-axis. Most of the time when we talk about this average rate of change, we think of the x-axis as being time going from here to here. What we want to do today is to turn that in not to an average rate of change, but to an instantaneous rate of change. So I'm not really interested now in what happens between A and B. I'm interested in what's actually happening at maybe some point C. What is happening here? Not what's happening from C to B or from C to A, but what's happening just at C. How fast am I going? Am I going fast? Am I going slow? Is my rate of change changing? Am I changing my rate of change? So what I want to look at is not an interval, but I want to zoom it in to say I'm not looking at a whole interval to get an average, I'm looking at a particular point. And this is that little artifice thing. It's a mathematical creation to have an understanding. It certainly has a work, but I'm not sure stopping something in motion at a particular point happens. There are a lot of things in ancient mathematical history, Zeno's paradox, for instance, about what was that about? The tortoise and the hare chasing each other. That's a nice thing to go back and look up. I don't remember it off the top of my head, but I know what it's about. So I'm going to take this average rate of change and look at this instantaneous rate of change. And if we look at our graph again, I got smart this time, I drew a few in advance. My average rate of change is going to be from that point to that point. That red line is going to represent my average rate of change over the interval from A to B. But I can also get an average rate of change from point A to point C. Or I can also get an average rate of change from point A to point D. I can also get an average rate of change from point A to point E. Now, we said as this point moves in closer and closer and closer, all of these secant lines are getting, these secant segments are getting shorter and shorter and shorter. What happens if I get this point, went from B to C to D to E? What if this point actually moves all the way to A? Then what I have at A is no longer a secant line, But what I have at A is a tangent line, a line that just touches the point, just touches the curve at exactly one point. Now, if you'll remember, the formula for this thing was f of b minus f of a, the slope, over b minus a. Now, what I'm talking about doing here is moving b down this curve, again making it closer and closer and closer to a. Well, if I do that, look what's going to happen. If my b moves to point A, what I have is f of a, f of b becomes f of a minus f of a, over b becomes a minus a. Now, most of you, if you just look at that, you'll say it's 0, but be very careful. That's 0 in the numerator, and a minus a is 0 in the denominator, and that's that little magic thing that keeps popping up in calculus. This forms 0 over 0, this indeterminate form. Well, what we're going to do is we're going to look at a formula. We're going to look at the definition. We already saw it last class. We're going to look at the definition of this thing that will generally give us the 0, 0 over form, and we're going to turn it into something that is going to not give us the slope of the secant line, but it's going to give us the slope of the tangent line at a point. So what I'm going to be looking at is not maybe the distance. Let's choose a point C here. I don't want to look at the rate of change from C to B. I want to look at what's happening. Oh, that's a bad one. I want to look at what's happening exactly at point C. And so I'm not going to have a secant line. I'm going to have a line that comes up here and just kisses off the curve. So here's the curve. I'm going to kiss off the curve, and I'm going to get the tangent line and the slope of the tangent line. So one of the very first definitions that you learn about the derivative is the derivative can be interpreted as the slope of the tangent line, the line tangent to the curve at a point. Now, as we looked at this last class, you remember we said we want f of b minus f of a over b minus a, and we wanted the limit of that as b approached a. And then we took that and we changed it around a little bit. You might want to go back and look at your notes from the last class. We changed b to some a plus h, and we changed a to x, and we ended up turning this formula into this f of x plus h minus f of x all over h. And this we are going to define, that's a little tick mark right there, as f prime, a prime mark, f prime of x, and that's the notation that we're going to use for something called the derivative of x, of f of x. Derivative meaning the rate of change. What is the rate of change of a function? Well, let's look at a particular function, something like x squared. If I look at a function, graph it like x squared, I can see, depending on where I am, different things are happening. If I'm at here, at this point right here, I'm going downhill. If I'm at this point right here, I'm still going downhill, but I'm not going downhill as steep. I've got a little curve right here. There's a point right here where I'm not going downhill anymore. I'm changing direction. I'm going from downhill to uphill. Here I'm going all right. Here I'm getting steeper and steeper and steeper. So you can see, depending on where I'm standing on this particular curve, I'm moving as I move from left to right, but the amount of change is different depending on the point. So the amount of change is not constant. Unlike, for instance, a linear function, if I'm here, I'm moving uphill. If I'm here, I'm moving uphill at the same slope. If I'm here, I'm moving uphill at the same slope. So I don't have any change in my rate of change here. Here I have a lot of change. If I get something like a sine curve, I'm going uphill, then I'm going downhill, then I'm going uphill. I'm getting a top point, I'm getting downhill. I'm noticing I'm curving, my curvature is changing here. I'm getting to a bottom point. I'm going back up to a top point. Depending on where I am, different things are happening to me. Well, we're going to define those different things, or we're going to describe those different things as an instantaneous rate of change. And the instantaneous rate of the change that is happening at the point is generally described by what is happening to the tangent line at that point. Now, for this point right here, what's happening? The tangent line is going downhill. So my derivative would be negative. Remember the slope? Slope is negative if it goes downhill. Slope is positive if it goes uphill. If I'm down at the very bottom here, it looks like my slope might not be positive or negative. My tangent line might be a horizontal line. Here it's increasing just a little bit. Here it's increasing a lot, but it's slowing down to get another 0 here. So where you are on the curve, that's a steep, that's not so steep, that's not so steep either, that's a little bit steeper, that's a little bit more steep. The tangent lines tell us how the point is changing, how the point is moving through the curve. And that's what I want to be able to describe, how a point is moving through a curve. Let's look, can you zoom in on this little example right here? Let's see what we can do with this. Yeah. Okay. Here's a nice little curve with some individual points on it. And the question is, match the point with the corresponding slope. Now, it's easy to match this because they're 1, 2, 3, 4, 5, 6, 1, 2, 3, 4, 5, 6. Everything here matches with something here. We don't have to do too much interpretation. Sometimes it might be hard to do this if we didn't have the specific numbers to match it. So let's look, if I'm looking for a slope, I'm looking for the slope of the tangent line. So what does a slope of -2 mean? Well, a slope of -2 means the line is going downhill. Left to right, the linear function is decreasing. Well, if I look at the tangent line at A, the line that is tangent to the curve at A, that's going uphill. So A is one of these down here. B, I really can't, looks like that if I draw the tangent line at B right there, let me get my tangent line back over here. Yeah. If I draw my tangent line at B, it looks like that's fairly horizontal. My tangent line at B here is not going up or down. C, if I draw a tangent line at C, it looks like it's going downhill. That's negative. And where else is it negative? Well, it's negative right here at F. So I've got two negatives. I've got C where the tangent line would be going downhill. I've got F where the tangent line will be going downhill. Now, let's see if we can figure out which of these two is which. This one is steeper or not as steep as this one. I think the tangent line at F is more steep than the tangent line at C. The tangent line at C is less steep. So it's going to be my interpretation right here that since the line at F, the tangent line is F, is steeper than the tangent line at C, then I'm going to let the point F be there and the point C be there. The next one is 0. Well, we hit on 0 a minute ago when we looked at B. If I draw a tangent line through B, it looks like it's a horizontal line, and remember the slope of a horizontal line is 0. So it also looks like B is on the top of that little hill, so I'm going to say that is B. Now, A, D, and E are the three positive ones, because if I draw a tangent at A, a tangent at D, and a tangent at E, I'm going to have slopes, tangent lines that are increasing, and tangent lines that are increasing are positive, or have positive slopes. So I have a 1/2, a 1, and a 3. Well, let's see if I can, I'm not real good at this, but let's see. Those are basically the tangent lines there. And the steepest one is going to be 3, the next steepest one is going to be 1, the next steepest one is going to be 1/2. So I think the steepest one looks like it's at A, The next steepest one looks like it's at D, and the least steep, the one that's most horizontal, the one that goes up the least amount, is going to be E. So I'm going to call that one E. This one was D, and this one was A. So that's an example of how we can describe points on a curve with the slope of their tangent line. The slope of the tangent line at A would be 3, and we could say the rate of change of point A would be 3 vertical units per horizontal unit, whatever the vertical units and the horizontal units are. The one that doesn't look like it's moving uphill or downhill is point B. Point B looks like it's at the very top of the hill for a second, and it's doing rest before it starts going back down on its little roller coaster ride. So we've got an example of a way to describe points with the slope of their tangent lines. Let's then see if I can find. I knew I was going to set it down a minute ago. Let me find my next little example that I wanted to do. Oh, that's it. Let's go to the calculator. Let's clear this out. Let's go to y equals, and let's clear that out. Another thing we can do for a slope, for the concept of slope here, and I like to do this one because it's a nice easy one to do, the sine of x. And on this one I'm going to zoom 7. If I zoom 7, that gives me a little trig where if you look at the windows, that's minus 6.1, that's almost 2 pi and minus 2 pi. And that value, 1.5707, is about pi over 2. So it gives you some, the intervals based based on pi. Now I want to look at the slope of the tangent line right here at this point. I've got a little bit of a problem with that because it really doesn't look like a tangent. I've got a curve going up like this, going up and then down like that, and I'm looking at the line that goes through. So back on the graph, if you'll notice it, back on the calculator, I'm not sure how I'm going to get a tangent line through here. Or it's not going to be tangent in the classic sense. Actually, it's going to cross the graph. It's going to be below the graph on one side of the x-axis and above the graph on the other. But it's not going to be a tangent line. A secant line. It will be, we'll still call it a tangent line, but it's not tangent the way we think of a line being tangent to a circle. So what I want to do is zoom in on that little piece right there. Now notice we've got nice curves this whole way, but I'm going to take this little center right here, this little center point, and I'm going to zoom in on that center point. And for this interval right between my fingers, from the interval from about here to here, you see the first little notch there and the first little notch here. That looks like a straight line to me. I've got a little bit of curve here, a little curvilinear motion here to see what's going on. If I zoom in again, let's see if I can zoom in again. I've taken all curve out of it. I have zoomed in enough to see that my straight line actually, my curved line actually, if I zoom in far enough, it's going to be, or at least it's going to be so close to a straight line I can't tell the difference. Well, that straight line that I see there on my calculator is the same as my tangent line. Any curve, even if you take a circle or something that's as curved as you possibly can, and you take a little small section of it, you zoom in on it, and you zoom in and you zoom in, eventually it's going to be so close to a line segment you can't tell the difference. So what I want to do is go back and look at some values on this curve. Let's go back to the calculator and look at some values. I'm going to trace some values here. And let's see if I can do minus 0.1. Let's get on that point right there. Okay, let me write that down. That's minus 0.1 is the x value, and minus 0.0998 is the y value. Notice those are almost the same. Those are almost the same value. This one's a little bit smaller than that one. This one's a little bit larger. Let's go to the other side. Let's do plus 1. Oops. I'm sorry, it should have been plus 0.1. Okay, and notice you expect it to be symmetric. 1.0998. So on my curve that's on the calculator, I've gotten those two ordered pairs, and it looks pretty much like a straight line. Well, what's going to happen if I find the slope here? Remember, the slope is going to be that in the numerator, the difference there minus the difference there in the numerator. So I'm going to say 0.0998 minus a minus 0.0998. The y value minus the y value in the numerator, the x value, that's 0.1, I'm sorry. 0.1 minus a minus 0.1. Well, that's a 0.2 in the bottom. I have no idea what this thing is in the top. I got to 8 and 8 are 16, put down your 6 and carry your 1. 18, 19, carry your 1. 18, 19, carry your 1, 1. Is that clear? Is that right? Okay. And I'm going to divide it. 2 goes into 19.9 times, carried 1, 19, 9, and 9 is 18, 16, 9, 9, 8. Well, of course, that is an approximation of the slope of the tangent line. Now notice that is very, very close to the value of 1. So if we go back to the calculator, and we look at a zoom feature, if I had actually chosen values closer here, like if you'll look at this one, this value right here, a lot closer than the 0.1, minus 0.0327, minus 0.0327. Now, at this point it becomes 2, and this point it becomes 1. Still rounds off to 2. That rounds off to 2. That rounds off to 2. But you get more and more decimal places that are the same the closer you get to that 0 point. If you get here, 0.00818, 0.00818, 12, 11. So the more you zoom in, if we zoom in closer and closer and closer, we'll get a line whose slope is closer and closer and closer to the magic number 1. Well, it turns out that the slope of the secant of the sine function at x equals 0 is 1. We'll see that later. That concept that we just looked at, that zooming in concept, sometimes it's called local linearity or linearization of a function. And we're going to be looking at that again in the next series of lessons. But what I want you to carry from here is that if you take any curve, no matter how curved it is, and you look at a section that's small enough, it's going to get straight, the line segment, the curve is going to get closer and closer and closer to a line segment. And that line segment is going to be equivalent to the tangent line. What I want to do now is to do some analysis. I want to use the definition of slope that the definition of the derivative that we've looked at to find the derivative of a couple of standard functions. Then we're going to look at a few numerical examples where we've looked at it graphically a little bit. We're going to look at it analytically a little bit now. And then at the end of the class, we're going to be looking at it numerically with some tables of numbers that we're going to look at. And I'd hope to be able to do a couple of examples of each before the end of this section. So the first thing I want to do after looking at the graph is to look at the definition. And you remember the definition of a function, the derivative of a function, f prime of x is equal to f of x plus h. Oops, I left the limit out. The limit as h, let me start that one over. Okay, f prime of x, which we're going to call the derivative, is the limit as h approaches 0 of f of x plus h minus f of x. Now remember, for the difference quotient, it was x plus h, that x value minus that x value. But we saw x plus h minus x, the x's cancel. This denominator just becomes a plain h. So we're going to be using this formula right here to actually find the rate of change of some particular particular curves. And the first curve I want to look at is the parabola y equals x squared. We're going to see some patterns with this thing. We're going to do x squared and x cubed, and we'll see what happens with the x squared and the x cubed. An interesting little pattern comes out. So I want to take the limit as h approaches 0 of f of x plus h minus f of x all over h. Now in this particular case, the function is x squared, so I'm replacing this with x squared. My domain value is still x plus h, so this becomes the limit as h approaches 0 of x plus h squared minus this, if I let that be the function, is x squared. And there are no x's down here, so that just stays as h. So I've done a substitution specifically for the x squared, where the function f of x is x squared, so that's this element squared minus this element squared. Now the nice thing about this is I can expand that in my head. The limit as h approaches 0, that becomes x squared plus 2xh plus h squared minus x squared all over h. So I did my binomial expansion right here. It's going to get a little bit more difficult when that becomes a cube or a fourth or a 20th power, but I can still do it. It just takes me, I'll have to get out my little table of Pascal's triangle, I guess, to get the coefficients. But, ooh, look at this. Isn't that neat? The x squareds cancel out. That is so neat. Okay, so what I really have here is the limit as h approaches 0 of 2xh plus h squared all over h. Now, we've said one way of solving it is just to do the substitution. So let's put the 0 in there and see what happens. Let's put the 0 in there. If I put 0 in there, that term h is 0, that term h is 0, that term h is 0. If I just substitute an h in there, a 0 in there for h, I get my 0 over 0 form. I got to keep working it because that 0 over 0 form isn't going to help me any. But I can factor out an h here. I got an h in this term and this term. So I'm going to say the limit as h approaches 0, I'm factoring out an h in the numerator, 2x plus h over h. Those h's cancel. That's nice. So I have the limit as h approaches 0 of 2x plus h. Now, what is this equal to? I don't have 0 in the denominator anymore. I got rid of that little stupid h in the bottom that was messing me up. Well, if h becomes 0, h has nothing to do with x. H is changing, not x. So this stays 2x. This is a constant in terms of h. It doesn't change. This becomes 0. And so I have 2x plus 0, which is just 2x. So we can say if f of x, now what was the function we started with? The function we started with was x squared. Then f prime of x, we just computed by the definition to be 2x. Now I know every one of you sitting here saying, oh, I just do the little exponent times the coefficient thingy and just do it. We need to see how the derivative, the definition of a derivative works here. We're going to do a couple more little simple examples before we start talking about the general, the rules for taking them a little bit more easily. Another one I want to do, if I can find my glasses, another one I want to do is, 1 over x. That's it, my favorite, the function that I'm getting ready to use 1,000 times. If f of x is 1 over x, what is its derivative? Well, we're going to do exactly the same thing we did a while ago. We're going to use the definition, the f of x plus h minus f of x all over h, and take the limit as h goes to 0. Except now our function instead of x squared is 1 over x, and we've got some fraction things to worry about. But we can handle that. It's just algebra. So let's say f prime of x is equal to the limit as h approaches 0. I'm back on the overhead now. There we go. The function is f 1 over x, and I can't help it. I have to write down the formula to start off with every time. That's something that was beaten into me, I guess, the first time I took calculus. Every time I do this, I have to write the formula down. I can't get away from it. Well, that's going to be equal to the limit as h approaches 0. Now, here's my function, 1 over x. There's my input value, so I'm going to say 1 over x plus h minus f of x is 1 over x all over h. And again, if I do a straight up substitution, if I just take this thing right here and substitute a 0 in here, I'll get 1 over x, that's a 0. 1 over x minus 1 over x is 0. H is 0. I get my 0 over 0 form again. So what we said earlier about the derivative being, calculus having a lot to do with the 0 over 0 indeterminate form was in fact true. Now what I want to do is get a common denominator in this numerator. And that's going to be the limit as h approaches 0 of the common denominator is x plus h times x. Let's see if I can do this. X plus h goes into x plus h, leaves an x. X times 1 is x. X goes into that minus x plus h. And that leaves an h in the bottom. So my next line then is going to be the limit as h approaches 0. Let me write the same thing a little bit more clearly. X minus x plus h all over x plus h, I guess it's not more clearly, all over h. Now I'm going to make this h over 1, do my invert multiply. So that means this h is going to go down here as a factor in the denominator. So that h became h over 1. I did an invert multiply and it goes right in here. So my next line, which is going to hopefully be a little bit more clear, is going to be h approaches 0, the limit. I'm going to get x minus x plus h in the top. And I'm going to get h times x plus h times x from the denominator. Now, all we've done is a little bit of algebraic manipulation. But notice what's happening again. If I take this 0, do a substitution, I get x minus x in the top, 0. I get 0 times all this in the bottom is 0. I still get my 0 over 0 form. I'm not out of that problem yet. So let's limit as h approaches 0. X minus x plus h is minus h. I got stuck on my distributive property there for a second. Here I'm going to say h times x plus h. I'm not going to change that at all, x. That's going to cancel. I knew something was going to cancel somewhere. I just couldn't find it. And that's going to cancel and leave a negative 1. So now I've got a nice limit as h approaches 0 of minus 1 in the top, x plus h times x in the bottom. Now I can do my substitution. I've gotten rid of that nasty thing that made 0 over 0. I can do my substitution. That's equal to minus 1 in the top. That's a 0. X times x is x squared. So f prime of x, if f of x is 1 over x, f prime of x, the derivative is minus 1 over x squared. So we've looked at a couple of examples. Let's look at one more little quick example. The example I want to look at is the square root of x, and then we're going to go back and look at these three problems. We're solving them using the definition. We're finding the derivative using the definition. Then we're going to go back and look at exactly what the derivative means in terms of the function. So if we look at the square root of x, let me give you a second. I'm going to let f of x be the square root of x. And I'm going to give you a second here to write down the formula. Write down the definition of the derivative in the formula with the square root of x. Let me give you a second to do that, and then I'll write it down. Okay, it's the square root of x. So that's going to be the square root of x plus h minus the square root of x all over h. Remember, square root is the function. I'm putting x plus h in it the first time, and I'm putting x in it the second time. So that's the function that I need to take the limit of. Sort of nasty. The first thing I see is I can't subtract square roots with different radicands in it. But, aha, clever me. I remember I didn't skip over that pre-algebra part, that pre-calculus part in the very beginning. Do you remember a way that I can simplify this? Conjugate. Yes, the conjugate. Very good. I want to take this expression right here and multiply it by the conjugate of the numerator. Multiplying it by the conjugate of the numerator would be the square root of x plus h plus the square root of x. So that's what I'm going to do. I'm just going to take this expression and do a little scratch work here. X plus h minus the square root of x over h. And I'm going to multiply that by the square root of x plus h plus the square root of x over the square root of x plus h plus the square root of x. I'm multiplying both the numerator and denominator by the same value. So this is 1. I'm not changing the value of the formula, I'm just the problem. I'm just changing the way it looks. The nice thing about this, that's going to end up being a distributive property. We're going to hope the h cancels. And that's going to end up being a FOIL method, a multiplication where there's no middle term. So let's look at the numerator here. The square root of x plus h times the square root of x plus h is x plus h. Doesn't matter what the outside and the inside terms are because one's going to be positive, one's going to be negative, they're going to cancel out. So that's going to end up being minus the square root of x. Oh, excuse me. Minus x. Square root of x times the square root of x is x. And in the denominator, I'm going to have h times the square root of x plus h plus the square root of x. And let's just do one more step on simplifying this thing. X minus x is going to drop out. That's going to make a 0. So I'm going to have an h in the numerator and an h times the square root of x plus h plus the square root of x in the denominator. And you can see what's going to happen. Exactly what I wanted to happen. I got rid of those nasty h's. That leaves a 1 in the numerator. So this becomes, now I'm going to put my notation back in, f prime of x is equal to the limit as h approaches 0. That was, after I did my algebra, that's 1 at the top. That's the square root of x plus h plus the square root of x in the bottom. Now I can do my little magic trick. Substitute the 0 in for h and just get the value out. Here, if that's 0, that's the square root of x. Here, that has nothing to do with, that's the square root of x. So the limit as h approaches 0 is equal to 1 over 2 times the square root of x. I've got the square root of x here, and I got the square root of x here. So if that's the derivative, if f of x is equal to the square root of x, then f prime of x, the rate of change, is 1 over 2 times the square root of x. So what does this mean? What does this mean? Let's look at, I'm going to go back a few problems and look at the y equals x squared before I come back and look at this one. But do you remember on the y equals x squared, the derivative was 2x. Well, 2x can be interpreted, that's our derivative, but remember we said the derivative can be interpreted as the slope of the tangent line at any point. So if I look at the slope of a tangent line, I'm going to choose some arbitrary points on the curve y equals x squared, and I'm going to compute what the tangent line should be. So let's look at the graph y equals x squared. Y equals x squared is, again, a nice parabola. And it looks like this. Now, the work we did a while ago, if I let y equals x squared, y prime is equal to 2x. That's the same thing as writing f of x and f prime of x. Another way of writing the derivative, this is basically from Leibniz notation. Dy dx is another way of writing it, f prime of x. These are three pretty standard ways of writing it. This one is going to come. This is probably the most useful in terms of some things in differential equations and separating variables that we're going to be coming to a little bit later in the course. But what does this mean? This means if I have a function y equals x squared, and I want to look at this point right here, that point right there is 1, 1. That point right there on the curve, if I let x be 1, y is 1, that point is 1, 1. I can find the slope of the tangent line. There's my tangent line right there. It comes along and just kisses the curve right at that ordered pair, 1, 1. And I can tell what the slope of that tangent line is. I can also say the slope of the tangent line can be interpreted as how fast that point is changing, the rate of change of that point. That point is changing. Well, if that point has a x value of 1, then we've said f prime of x is equal to 2x. So f prime evaluated at 1 is equal to 2. The slope of that tangent line, the slope is 2. Now, if we go on up to 4, I would expect that tangent line to actually be steeper. So let's look at that example. Again, I've got a parabola, and I'm looking at the ordered pair 2, 4. And I want to know what the slope of that tangent line is. Well, it's the same function. F of x is equal to x squared. So f prime of x is equal to 2x. So what I want to do is take the x value right here to find the slope of the tangent line, because that's all it requires. F prime of 2 is equal to 2 times 2 is 4. So the slope of that line is 4. What would we expect over here? Let's take the point minus 3, 9. If I have the point minus 3, 9, here I would expect the tangent line to have a negative slope. Well, exactly the same thing's going to happen. F prime of x is 2x. So f prime at negative 3 is negative 6. And the slope of this line right here is negative 6. So if we're looking for slopes of tangent lines or rates of change of a point, I can say the point at 2, 4 is changing 4 units, whatever the units are. 4 vertical units for each horizontal unit. We haven't given them any type of name for the units. But the rate of change is 4. 4 miles per hour, 4 feet per second, whatever the units are. The rate of change is 4. Let's do another one just like that when we did the 1 over x. F of x was 1 over x. And I believe we found f prime of x to be minus 1 over x squared. What does that mean? That means, let's look in the first quadrant here for the graph 1 over x. And let's look at the point 1, 1. If I put a 1 in here, I got a point 1, 1 right there. That looks like it's the point that's closest into the origin. I want to find the slope of the tangent line. So I'm going to actually draw the tangent line right here. Now I can tell from the graph that that tangent line has a negative slope. Well, that's probably coming right from this little thing right here. I'm going to just choose the point 1, 1, and I'm going to take the x value to substitute in here. Well, f prime of 1 is negative 1. If you square 1 at the bottom, you get 1. It's a negative 1. Let's go out here, say a point 2. Now if we go out to the point 2, the ordered pair is 2, 1/2. Notice in actuality it doesn't really matter what the y value is. All I'm doing at this particular time is substituting in. So the slope of the tangent line here should still be negative. Well, that's where it's going to get it from that right there. But it's also going to be a smaller absolute value number. It's going to be more of a horizontal, and if we substitute a 2 in there, f prime of 2 is equal to negative 1/4. And as you go out, you can see, you can imagine that the slope's getting more and more and more and more to be a horizontal line. The same thing's going to happen over here. This is interesting. If I look at the point, say negative 1, -1 right here and look at the tangent line, I'm going to get the same thing. F prime of -1 is still a -1. -1 in the denominator, -1 squared is +1. So the slope here is still a -1, and that's what we expect to happen. It's going downhill. These two lines, it's not a very good rough drawing here. These two lines I think should probably be parallel. Since their slopes are the same, the line should be drawn to be parallel. It's just not to scale. So we've looked at some interesting little derivatives, found the derivatives using the definition. One of the things that we're going to be looking at tomorrow, the next series of lessons, is how to take a derivative without using the definition. There are a lot of little techniques of finding derivatives, both for polynomials and for lots of different types of products, quotients, trig functions, exponential functions, lots and lots and lots of kinds of functions. And we're going to learn them all. What I want to do now for the next little part here is we've looked at the slope of the tangent line graphically. So the derivative slope of the tangent line, we've looked at it graphically. We just looked at it analytically where we actually work the algebra. What I want to do now is look at it numerically where we have a bunch of numbers but we don't actually know what the equation is. One of the things that has happened probably in the last 120 years or so is that mathematically is that we're able to gather data on what the actual values are, but those values are hard to turn into an equation. Sometimes we can get close to an equation, but we can't actually get the equation. And sometimes we can't even get the equation. Sometimes we can just find the rate of, we can find actually its derivative and have to work backwards to find out what the equation is. So I've got a couple of examples here that I'm going to be working on the calculator. And on the calculator, I'm going to be using to help with this some ordered pairs that I'm actually going to give you. Now, as we're looking at these ordered pairs, let me get rid of that. As we're looking at these ordered pairs, I'm going to be just entering them one at a time to show you how to enter them. They will be in a list on the web page if you want to go in and if you can't follow, if I'm going too fast for you on the tape, these numbers will be listed as an example on the web page. But on a particularly cold day, let's see, I've got to, okay, let me get here. I'm using the stat feature right here because I'm going to enter a bunch of numbers, a bunch of ordered pairs. So I just mash the stat button and I'm going to go to edit. Edit is going to actually allow me to enter values here. So at time equals 0, my body temperature on this particular cold day was 98. A little bit later, after a minute, I cooled down a little bit to 94.85. A little bit later, well actually I guess by the time I get here I'm dead, so maybe this isn't me, but it's something decreasing. After 2 minutes it drops down to about 93.06. After 3 minutes it drops down to a 91.9. After 4 minutes it drops down to a 91.17. Notice it's decreasing, but notice in these values right here, the amount of decrease is decreasing. This first amount of decrease, the amount of change from 98 to 94.85 is a little bit over 3. But here the change is still getting lower, but the change is not jumping the same amount. The amount of decrease is decreasing. So what we're looking at there is something we're going to be talking about later, is the rate of change of the rate of change. If the rate of change is the derivative, what do we talk about when we talk about the rate of change of the rate of change? So, excuse me, we're looking at values going down. There's 6, 7, 8, 9, 7 and 8. After 7 minutes, it drops to 90.28. Notice now the difference here is about what, 0.17, 2, 3, 4, 0.17, and then the difference here is about 0.11. So again, the rate of change is changing. Now I want to take these particular points right here, and I want to graph them. I'm just using the calculator to graph them. The calculator graphs a lot better than I do. So on my calculator, I have a statistical plot feature. So I'm going to hit second statistical plot. And on stat plot, this is the first one I'm going to do. So I'm going to turn it on. Right now it's off. I'm going to turn it on. I get a choice of types of functions. I'm going to choose this one. I'm going to come back in a little bit and choose that one. But the first one right here, oops. If you look at this one, this is just the individual dots, and that's the one I want to choose. My list, if we go back, we'll look at them in a second. My lists were L1 and L2. Those are basically the default lists. And then I have a nice little choice down here. Do I want my dots to be little squares? Do I want my points to be little pluses? Or do I want my points actually to be dots? I'm going to choose them to be little pluses. Now on my window, I'm going to have to change the window a little bit. The X values were 0 to 10, or 0 to 9. So I'm going to go 0 to 10, get a little bit extra room in there. My scale is 1. My Y minimum, I basically went from 90 to 100, so let's go from 90 to 100 to get them all in there. My Y scale is 1, and let's graph it. Okay, I don't like the way that graph looks. It's a little bit too close down over here. So what I'm going to go back in and do is change my window a little bit. So my Y, instead of going from, let's say my Y goes from 85 to 100. Yeah, that gives me a lot better looking graph. I feel much more comfortable with that. So I'm back on the graph again. Thank you. Notice what's happening is I'm decreasing as my ordered pairs went along. As X got larger, the Y value got smaller and smaller. But notice the skip between 1 and 2, 2 and 3, 3 and 4. The jump is getting smaller and smaller and smaller. Now, what I want to do is talk about the rate of change. If I talk about the average rate of change, remember the average rate of change over the whole interval from x equals 1 to x equals 8 is a big tangent line. So I can actually talk about the overall rate of change, which I'm going to do, and then I'm going to choose a particular point and try to compute an instantaneous rate of change for a particular point. So if we'll look back at the graph again, I'm going to trace, and the first point the first point we had was 0, 98. So I'm going to write down the ordered pair 0, 98. You need to write that down also. And then I'm going to go to the far right. Notice every time I hit trace here, every time I hit the cursor, I'm going to the next one. 8, 90.17. Now, if I use those two ordered pairs, 0, 98 and 8, 90.17, that will give me the slope of the line that connects this endpoint to this endpoint up here. I hope you can see it flashing. And that will give me the average rate of change. That will give me the average rate of change. So back to the overhead. These are my two ordered pairs. And the average rate of change, I expect it to be negative if I say 98 minus 90.17 over 0 minus 8. That's just the regular slope. That's the slope of the secant line. And that value right there will give me my average rate of change over the whole interval from 0 to 8. Well, let's see what that is. That's it's a negative 8 in the denominator. That's 8 minus 0.17 is 7.83. I would just go ahead and leave it like that. We can get the calculator here and multiply that out. 7.83 divided out, I guess, divided by 8 is negative 0.97875. I left the negative off. The 8 was negative. That's just the number. We need to put the negative with it. So that's the average rate of change. That's about 1, negative 1. So if we go back and look at the graph, if I connect this point, I don't like that point. I'm back to the calculator, I'm sorry. I don't like that point hiding up in there. So I'm going to have to do this right here. I'm going to say like a minus 1. And then graph it again. Oops. And there's the point right there. We can see the point. If I connect the dots from here to here, the slope would be about negative 1. But notice if I get my little tangent line right here, at that point the slope is pretty steep. At this point the slope is less steep. If we sort of followed what the curve going around would be, the slope is getting less steep and less steep. So let's choose this point right here. What's that? 0, 1, 2, 3, 4. Let's choose the point when x is 4 and see what we can do about using these numbers to find an approximate slope, a numerical approximation to the slope. Sometimes we don't have the equation. We have to use a numerical, just our best guess. Well, I'm going to go back to on the calculator, I'm going to go back to the actual values at 4. And there's several things I can do with this. I can find the slope between 0.3 and 0.4. I can find the slopes between 0.4 and 0.5. And this will be the slope going in from 3 to 4. And this will be the slope coming out from 4 to 5. So that's what I'm going to do first. I'm going to find the slope between the ordered pair where x is 3 and the ordered pair where x is 4. So let me write those down. That's 3, 91.9, and 4, 91.17. And then I'm going to write down the slope for 5, the ordered pair for 5, 90.73. And what I'm going to do is find the slope for those two, and then I'm going to find the slope for those two, the little secant here and the little secant here. And that right now is about as good as I can hope to do. So 0, 1, 2, 3, I'm going to find the slope between that point and that point. Then I'm going to find the slope between that point and that point and see what happens. So I'm back now on my calculator. So I'm going to do the for 3 to 4, so that's going to be 91.9 minus 91.17. And I'm going to divide that by 3 minus 4. And so the slope between the point at x equals 3 and the point where x is 4, that slope is minus 0.73. Now I'm going to do the same thing between the 4 and the 5. Let me clear that. I'm going to say from the 4 is 91.17 minus 90.73. And I'm going to divide that by 4 minus 5. That's minus 1. Oops, what did I do wrong? Oop, wrong minus. I always get that minus wrong. Minus 1. And that's minus 0.44. So what we can say is, if I go back and look at the graph, what we can say is the slope, notice the slopes are both negative. The slope between 0.3, 0, 1, 2, 3. The slope between here and here is a little bit steeper than here to here. This is 0.7, minus 0.73, the secant line right there. The secant line right here has a slope of minus 0.44. A good guess might be just somewhere between those two. Does that mean the real answer is going to be the arithmetic mean, the average of those two? and it's certainly not. It's not necessarily going to be the average, but the average would be a good approximation, and sometimes that's as good as we can do. So if I take the 0.73 and the 0.44, minus 0.73 minus 0.44, and divide them by 2, an approximation for the slope there would be about minus 0.585. So that would be a way of giving an approximation of a slope if you just had numbers. The tangent line, if you look at the graph on the overhead again, this is overhead. I'm sorry, the overhead.
Okay.
Oh, that's fine.
We need to wrap this one.
Okay, I got 5 more.
Like 30 seconds.
30 seconds? Okay, the slope's right there. We'll see you next class.